To get access to the Network Plus notes as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. All right, so troubleshooting. Network troubleshooting is probably going to be one of your biggest responsibility sets as a network administrator, as a network engineer. And this is a big topic. I think it's one of the more important topics. There's a lot of weight around this topic when you look at the Network Plus exam as a whole. And really, it's just, I think it's an important conversation because it's not really the most fun part of networking, and setting up a network is more fun in my opinion, and the initial infrastructure setup and all of that stuff is a little bit more fun than troubleshooting for whatever reason. And this might be a personal thing where it's like I don't like troubleshooting, but it happens to be a really big element of pretty much everything that's done in IT. One of like a bulk of our responsibility, probably 70% of our responsibility in any subcategory of IT is going to be troubleshooting for whatever our specialty is going to be. So network troubleshooting is no different. And under this chapter, the very first subsection that we're going to talk about is the troubleshooting methodology. So there's actually a series of steps that you can take as kind of like a template, or as an approach, as an overview, an outline of an approach that you can take towards troubleshooting any kind of an error. So this is the outline for the actual approach, the template for the actual approach. And just as kind of an overview of this concept, excuse me, I'm kind of losing my track here. So we have troubleshooting is a systematic approach to diagnosing and resolving network issues. A structured methodology minimizes downtime, prevents recurrence, ensures efficient resolution of complex problems. And the core steps are these. We have identify, isolate, and resolve. And then these actually break down into finer steps that you can take. And these core steps form the foundation of effective troubleshooting. So you identify the problem, make sure that you actually know what it is, and then you isolate it. So you hone in on it, and then you prevent it from spreading to the rest of the network, and then you resolve it. And this also applies to, this can also be like a cybersecurity methodology as well. You identify what the attack is, you isolate the compromised machine, and then you resolve and wipe it or do whatever you need to do to mitigate it and clear up the compromise or the exploit that is on that specific machine. So this is a pretty solid approach to pretty much everything that we do in information technology. It just so happens that it's not that simple, right? So there are different steps that you would need to take to identify something, and then to isolate it, and then to resolve it. So this is the overview, right? This is the general approach. And now we're actually going to look at the finer details, the actual step-by-steps of this. Step one in the troubleshooting process is to identify the problem. So you need to understand the issue by gathering information and defining its scope, meaning how far it's spread, what is actually the elements of this thing. And you gather essentially as much intel as you humanly can gather, and you gather it from as many sources as you possibly can, because you don't want to misdiagnose. This is one of the big elements of identifying. If you actually have done a good job of doing the research to identify the problem, the rest of it becomes easy. The rest of the troubleshooting process becomes relatively easy. If you have not done a good job of identifying the problem, then you'll have to go back to the first step and try to re-identify the problem, and you just keep repeating that process until you've gathered the information to try to identify the problem. Now, you can initially gather as much information as you can, try to do the next step of the isolation, and then you'll just based on the new information that will be presented to you through the remaining steps, you'll be like, oh, you know what, this actually adds to my understanding of this, and then you can go hone in a little bit further on whatever the problem is going to be. So I would say spend the most amount of time as you can in the initial identification phase so that you can gather as much information as you can, and then from there you'll try to expand your knowledge base as you go along with the troubleshooting process. And the better of a job that you do at this, the easier the rest of the stuff becomes. The actions for identification are to collect information, right? So interview users experiencing the problem to understand the symptoms and timing, gather logs from devices, error messages, or alerts from monitoring tools, and document the issue for clarity. So create essentially a case binder for this, or a case document for this, and you compile all of the information that you've gathered from the users, from the logs and the devices and the error messages and monitoring, all of that stuff. You collect as much data as you can. Then you define the scope. And so this is to determine if it's just implementing or affecting a single device, if it's affecting a specific segment of the network, or the entire network in itself, right? So how widespread is this specific issue? And then you identify any recent changes that might have triggered the issue. So was there a recent update that we had for these machines, and was it after that update that the problem started arising? Or was there some kind of configuration that was made, and that configuration log that we were talking about, the digest of all of the configurations that have been made or the changes that have been made, this is why it becomes very important to document everything, as we talked about in the documentation section. You need to be fully aware of everything that has been done in the network, so that in case there is a problem, you can backtrack and you can try to find out where the problem started, right? And then you verify the reported issue, which is reproducing the problem if you can, to confirm that it actually exists, and then find the details of it and log the details, document the details, to actually confirm that that is indeed the problem that you think is wrong with the network or the devices or whatever. So the example would be that a user reports that they can't access the internet. You verify that their device cannot resolve domain names, suggesting a potential DNS issue, and you need to check to see if the rest of the devices in that user's segment, so in their office, let's say, you need to confirm if the rest of the devices in their office can access the internet or not. And if the rest of the devices can access the internet, then you can say, okay, well, you know what, it's probably just this one user's device. If the rest of the devices inside of that office cannot access the internet, okay, well, can this in this overall department or this region, can they access it? Are they having the similar issues? If not, then we need to hone in on that specific location. If everybody else is also having that same DNS issue, then there's something wrong with our configuration in our network as a whole. So this is how we can identify it, right? The user reports it, so you collect the information and then you define the scope. You need to make sure whether or not it's just that user's device, or if it's their office, or an entire network segment for that region, for the LA region, or for the United States or something. You know what I mean? So you need to hone in on how widespread this specific thing is. So all of this falls under the identification portion of this troubleshooting methodology. The next step is to establish a theory of probable cause. So develop your hypothesis, right? Develop the theory about what the root cause of this particular issue is. And this is still falling under the identification, right? So if we were talking about identify, isolate, and then remediate, or resolve. If we were talking about those 3 steps that was in our overview of this section, we're still technically inside of the identification stage. So the theory establishment, or developing the hypothesis, breaks down into first starting with simple explanation. So check for basic issues like disconnected cables, for example, or power failures, or was there a recent update, etc. Then you leverage tools and data. So use the network monitoring tools, use the logs that you got, use documentation, so network diagram configurations, to support the theories that you've developed, right? So based on what you think went wrong, you gather all of the intel, and then you see whether or not the intel supports your hypothesis. And then you apply those knowledges of the OSI model that we gathered at the very beginning of this. So you would map the issue to the relevant OSI layer. So if it is indeed a DNS issue, then it's obviously not layer one of this whole thing, right? It's not on the actual physical layer, and it's probably not on the data link layer. It's getting a little bit further into the network layer where IP addresses are getting resolved to domain names and probably beyond that. So you see, based on your theory and based on the intel that you've gathered, what layer of the OSI model does that problem connect to, and then that will allow you to hone in further to try to see where you need to go to actually resolve the issue. So you would map the issue to the relevant OSI layer, so layer 1 for physical connectivity, layer 3 for routing, etc. So the example of this would be if the users can't access a web server, the problem might stem from a DNS misconfiguration, firewall rules, or server unavailability, right? So there are multiple reasons why a DNS misconfiguration could happen, or why a person cannot access a web server. Now, if they can't access the web server specifically, but they can access the rest of the internet, they can go to Google, then you can say, okay, well, it's not our overall DNS configuration because at least they can access Google. So maybe it's not the DNS issue at large. Maybe it could be a DNS misconfiguration for their ability to access the web server. Maybe there hasn't been some kind of a resolution or a DNS resolve that is applying that IP address of the server to the domain name of the server. Maybe that's what it is. Or maybe we have a firewall rule for whatever reason that is blocking this user from being able to access that web server, or it's blocking the web server from being accessed by anybody in this user's level, maybe, or from this user's location or subnet, maybe. Or maybe the server is just down, right? So it could be a variety of different reasons why a web server is not available. So these are parts of the theorizing. This is for us to develop the hypothesis, right? So if you can't access a web server, it could be a number of reasons why you can't access a web server. And then once we have the overall list of reasons, we can try to hone in on what the most likely reason is, and then use the data that we have to try to support that hypothesis. And then based on that, you can try to see where you would go to resolve the issue. Once you have your hypothesis or your theory, you need to test it. You need to see if this actually is the theory that would be the root cause of what's going on. So you would validate or rule out the theories by testing potential causes. So if we think that the web server could potentially have a DNS issue, it could be a firewall rule, or it could be that the server is down. Let's say those are our 3 theories. We need to test all of them to see which ones should be ruled out and then what the actual cause is. So conducting these tests is where these various tools comes in, right? So you would use ping to see if there's any kind of a response that comes from the web server. And if there is a response that comes from the web server, okay, so maybe the web server is not down. You would use traceroute to see how many hops are being taken from your current IP address to the destination IP address and what the route is that those packets are taking, to see at what point, if they're being dropped, if there's any loss of packets. And then of course you can have a packet analyzer like Wireshark that would also help you to test the connectivity and identify bottlenecks in the network connection or the traffic. And then you would perform specific tests that are relevant to suspected issues. So DNS lookup tests for resolution problems. So if the IP address is not resolving to the domain name and people can't access the domain name, maybe it's that there is no resolution. The actual resolution of this, meaning a DNS resolve, is not taking place. What happens with DNS resolve is that the IP address is now resolving to a domain name and vice versa. So then you would use a tool like NSLookup, for example, to see if I do NSLookup and then I give it the IP address, does it actually resolve to the domain name? Or if I do a NSLookup and give it the domain name, does it actually resolve to the IP address? And that's one of those very, very basic troubleshooting tests that we can run to actually see if maybe that's the issue. And then if it's not, if it actually does resolve, then we'll go to something else to try to see what the problem might be. Then you would eliminate all the possibilities, right? So if your theory is invalid, you document it and you make sure that you have jot it down or put it inside of a document or something like that. That's like, okay, out of all of these theories that we had, these 5 are not the the case because we tested it and these weren't the reasons why the network is down. You know, these tests actually passed and there was nothing wrong when we ran NSLookup and the DNS resolution was fine. So it's definitely not this. There's something else that's going on, right? So you eliminate whatever possibilities you can so that, again, you can narrow it down and you can hone in on the actual problem. So traceroute test reveals that packets fail to reach their destination at a specific hop, indicating the routing issue and where the packet loss starts to occur. So traceroute is a really common test that you can run to see where those packets fail. Now, assuming that all of your tests have actually gathered or they've divulged really good information and you really have honed in on what the problem is, then you can actually go into creating your plan of action and then executing your plan of action. So what would you do to resolve the issue, right? So we've gone from identification, we've isolated the problem by doing various tests, and now we are going to develop a plan of attack, right? A plan of action to actually go ahead and resolve this issue. And this is based on the confirmation of what those root causes are. So you've done a lot of testing, you've eliminated all of the incorrect possibilities, and you know exactly what the problem is. And now you can actually develop a plan of action. So you would define clear steps that you have to take. So any configurations that you need to make, hardware replacements that you have to do, software updates that you need to do. You would plan for minimal disruption to users during resolution. So as we are resolving this, we need to make sure that we do it. Let's say if it's you need to do an entire revamp of all of the software inside of the entire network, then you do it outside of business hours so that it doesn't affect anybody, right? Or you do it on the weekend when nobody shows up to work because you guys are closed on Sundays, something like that. You would do it in a way that it does not disrupt the users. It does not prevent them from actually doing what they need to do for business activities. And this is a really, really big deal. The most common version of this is, think about if you've ever changed your internet service provider and you're like, okay, well, I don't want to lose internet. I don't want to lose internet service. So what I'm going to do is I'm going to have my new internet come first, and they would set up everything and we make sure that that's up and running before I cancel my old internet, because I don't want to have a lapse of service, right? And that is one of the most basic ways to plan for a minimal disruption to you, the user. So then you create a rollback plan. So you would need to have some kind of a contingency plan to revert the changes if your resolution fails, right? So have a super recent backup of everything. Make sure that at the very least, whatever is currently going on, you have some kind of, unless like none of your systems are working, then I mean, you would go to the most recent version of your update or your backup where things were actually working, and that would be your contingency plan. But if things are working, it's just there's some kind of an issue that's going on that you need to resolve, then you would have at least your contingency plan being right now. So you would have all of your backups as of now. If not, you would go back to the most recent backup or the most recent patch update, software update, where things were working. And then that would be your revert, your rollback, right? That would be the rollback. And then from there, you go through your resolution attempts, and if the resolution works, great. If not, at least you have a point of your service or point of your system where you can roll back to just make sure that it still does work while you go back to the drawing board and try to figure out if you can find new resolutions. The example of this would be if the issue is a misconfigured firewall rule, then you adjust the rule to allow required traffic and then test the access immediately to just make sure that nobody else can get through and only the people that should get through do get through. So a misconfigured firewall rule is not as bad as something that may have happened that requires the entire revamping of your entire network software or operating system or something like that. Firewall rules are a little bit easier to manage because you can just add, look at your list of firewall rules. If a segment is being blocked off, you say, okay, well, we want to first have a deny all that goes in, and then we do an explicit allowance of this particular segment to make sure that as we're doing this resolution, no malicious actors can enter in to our network. And so we deny everybody, and then we just explicitly allow this one particular segment or this one particular subnet of IP addresses etc. So you can still establish your rules for your firewall, or the whatever changes you're making to your network, by taking that zero trust type of an approach, by taking that, okay, we're going to still take like the absolute bare minimum of trust, or bare minimum of access, or whatever it is for your given situation, to make sure that as you're making your changes, actual malicious actors can't enter the network, or they can't try to get into the building, or whatever it is, right? So all of these things can be done with the highest level of paranoia to make sure that nothing bad actually happens while you're going through your resolution attempts. Once you've implemented the resolution and tested the resolution, you would take your systems back to online mode or business as usual, and then you just verify that the system is actually fully functional. And this is making sure that the issue is actually resolved and it has not introduced any new issues or any new problems. And you would do a variety of different scans, and you would monitor the network traffic, and you would probably just look at everything for the next few days or the next few weeks, depending on the size of the network. And you just want to make sure that whatever you've done is working as it's supposed to, and it has not introduced any new issues. So one of the big things of this is, of course, performing tests. So there's the performing of the test in some kind of a sandbox environment before you get to this stage. But then once you're actually putting your systems back online, you need to continue to do tests. You need to recheck all of those affected systems or subnets or network segments, and verify that they're actually functioning the way that you think they should be. And then you would test any related systems to confirm that there's no unintended impact and there's no collateral damage, right? And then you would involve users. So ask the affected users to confirm that the issue has been resolved from their perspective, and the things that they need to do, or the things that they were originally trying to do that they couldn't do, now they can actually do, right? So this is, it kind of goes hand in hand. You would do your tests on your end, and then you would ask whatever the users that originally reported this problem to you, you would ask them to also run tests and confirm to make sure that all the things that they need to access, they can actually access. So after fixing a DNS misconfiguration, you verify that the users can actually access the website and they can do DNS lookups. For them, it's not really, oh, can you see if you can do a DNS lookup? It's more like, hey, can you open your web browser, see if you can actually access the web server? Can you access Google? Can you access your email? All the things that they were trying to originally do, see if they can actually do it now. Step 6 is technically to document the process, but I feel like you should be documenting throughout the entire thing. So as you get a problem that has been reported to you, you document it. As you go through your identification, intelligence gathering, your isolation, all of those things, your testing, you document all of that stuff. As you develop a plan of action, you document it. As you implement your plan of action, you document it. As you test after your implementation, you document all of that. So the whole thing should be documented. There should be a case file that creates for essentially every problem that's been reported to you. In small cases where there's like some kind of a support request, there's a ticketing system that is always used for desktop support environments, and then they create these cases for every ticket that is reported to help desk, or it's reported to IT or the network admin. For that ticket, there's a case that's been created, and then once that situation has been resolved, the case is then closed. But at least there is some kind of a trail, maybe not a physical paper trail, but there's some kind of a digital paper trail that exists that has every single step of that support ticket and every single step of that troubleshoot has been documented for future reference. And management needs to look at this, auditors need to look at this, and all of these things need to be confirmed. And if the same problem arises in the future, we need to know what we did to solve it. And if it's an advanced version of the problem, we need to know what the last update was or the last patch was, and why there is the problem is re-arising. Like what is the reason? We thought that we had already solved this. Did we miss something the last time that we did this? So there's a lot of different reasons for proper documentation, and it's one of those things that will not only be, it's like kind of a compliance thing, but it'll save your ass. Like if you have really good documentation, detailed documentation, it'll save your ass in the event that something like this happens again, and then your management is like, well, you were the one that was in charge of this last time, what did you do? and then you just pull up all of your documents and you're like, yeah, this is exactly what I did. These are the steps. This is the date, the timestamp of all the steps that I took. And then they look at your work and they're like, okay, well, you did everything that you should have done. So that's fine. So let's see what else happened, or maybe what was it that was missed, or did a new problem come into play? The actions for documentation would be to log the details. So document the issue, the root cause, the actions that were taken, the results, note any lessons learned or recommended preventative measures, update the documentation. So revise your network diagram, your configurations or knowledge base if necessary, update your playbook if necessary. Usually there's some kind of a playbook or a user's manual that's available to every single person that's inside of IT, so that they know where to go to find solutions if necessary. And then if the solutions that are already inside the playbook or the manual don't work, you need to add whatever did work. After you've resolved the issue, you update the playbook, you update the manual, so that everybody else is in the loop and they know what to do in the future. So documentation is a big step of the troubleshooting process. It's one of it's like the one step that applies to every single type of troubleshooting, whether it's cybersecurity, network stuff, whether it's systems or operating systems or anything of the sort. Documentation is a big deal. For penetration testing, documentation is a big deal. You know, this is the scope. These are the different machines or the different segments of the network that we're allowed to attack. This is what we plan to do. This is the recon that we've done, and this is the intelligence that we've gathered. These are the operating system versions and the different services that they're running, and these are the vulnerabilities that we found. Like, all of those things get documented as you go along. You don't wait until the end of the process to document. You document as you go, because there's just too much information to try to remember at the end of the whole thing. It's like you're not going to remember everything, I promise you. Unless you have an insane memory, you're not going to remember everything. And when I do penetration tests, or when I do any kind of vulnerability scanning or troubleshooting, my documents, like for that specific test, ends up being 30 pages, 50 pages. Like, these are not short documents, because you are doing so many tests. And if you're copy pasting the error messages, and if you're copy pasting the versions and all of the plans and everything, once you start compiling everything inside the same document, this will not be a short report. The full report is going to be dozens of pages. Maybe you'll have a summary that's like 2 pages, but the full report itself, that includes all the troubleshooting, all of the error messages, all of the things that you've gathered, that's going to end up being dozens of pages. So you're not going to remember all that. Like, it's just not gonna happen for anybody. So you just need to start documenting from the very beginning. Keep documenting at every step, so that by the end of it, you have a full case file that has all of the details of everything that went down. So a troubleshooting log helps to resolve similar DNS issues in the future by providing a clear resolution process, and that's just one of the benefits of this. Compliance is another one. Management wanting to audit your work is another one. Making sure that you can just look back and be like, okay, I did a great job. That, like, there are so many different reasons to do this. And one of the key reasons is that if somebody in the future is taking over your role because you got promoted or you moved on to a different company, there is some kind of a log, some kind of a manual that's left over. So for that new person to know, in case any kind of an issue like the one that you dealt with, in case that shows up, then they know what to do and where to go to resolve that problem. To summarize everything that we just talked about, there are some best practices that you can always just think about. Think of this as like a checklist, as a mental checklist or something to just always keep in mind when you're thinking about troubleshooting network issues. And the first one is to use the OSI model as a framework or a reference. So start with physical connectivity, which is layer 1, and then move up the layers to isolate the issue. So if everything on the physical layer is fine, if the network cables are fine, if the Ethernet cables are fine, if the power cables are all good, if the devices themselves are all good and nothing's shut down, if all of that stuff is good, then you move on to the next layer. And then if all of the stuff on layer 2, the data link layer, is fine, then you move on to the next layer, and so on and so forth. So you use the OSI model as the ultimate framework, and you just go up each layer one by one until you actually can isolate whatever the issue is. And to help make this a little bit easier for you, you use tools, right? So Ping, Traceroute, Wireshark, SNMP, All of these things provide critical insights for troubleshooting. Those scanners that we talked about earlier when we were talking about the physical devices that you can actually connect to the wiring of your internet box or something to see if along the 100-foot wire that goes from outside of the building to the inside of the building, if there's somehow a disconnect or a cut along that wire or any of those things. There are so many different things that you can use apart from these logical tools, these software tools like Wireshark and Traceroute. Apart from that, there's actual physical tools that will also help you try to pinpoint where the issue is and isolate where the issue is. Then you prioritize the issue. So address problems affecting critical systems or large groups of users first. And that it's a little bit of a common sense kind of a thing. But if it's affecting your main web server where everybody needs to be able to access the web server to be able to run the business, like the business won't be able to operate without your main data servers and your web servers, then you need to address those things. If there is if the entire west coast of your company is down for whatever reason, and then you have 5 people on the East Coast, unless those 5 people on the East Coast are the actual C-suite executives, which they will also tell you, you know what, no, fix everybody on the East Coast because there's thousands of employees on the East Coast that need to be up and running. And then you can come and address our issues for our 5 little computers. Until then, we're going to work from our cell phones or whatever it is. It's like even the C-suite people will be like, no, you need to go address the issues of the many, right? The needs of the many far outweigh the needs of the few. And this is an exact example of that. Then you want to collaborate and escalate. So work with team members or escalate to specialized support if the issue requires additional expertise. Don't be proud in this thing. Don't try to take all the credit for yourself. It has nothing to do with that. The faster that you can get up and running, the better it will be. And if you can actually learn to leverage team members or escalate when you know that you're out of your depth, that is a sign of leadership. That's actually a very powerful attribute of a good leader, that they know how to work with other people, how to leverage other people to get the work done. And you will most likely get recognized and promoted faster if you actually know how to do this, if you can actually collaborate and learn how to escalate to experts on given subjects instead of taking the entire load by yourself because you think that you need to own all of the credit or whatever the reasoning is that people do stuff like that. And then, of course, prevent the recurrence. So implement changes to address root causes, improve network resilience, document everything as it happens, document all of the resolution steps that you took, finalize whatever the actual resolution is, make sure that everybody is aware that, hey, in case this happens again, all of this stuff is inside of this document, share it with everybody. There's a very, very important, there are a lot of different ways that you can actually prevent something from occurring again. And the majority of that has to be make sure you actually implement your mitigations, but also document everything that you've done and then let management know, hey, I have everything that just happened. I have a document. And most likely your management will tell you, yeah, you need to, once you've documented everything, you need to add it to our playbook, the general playbook for the networking department, or you need to add it to our manual or whatever it is. Like for the most part, they'll tell you where to add the resolution steps to. But if they don't tell you, make sure that you save a organized copy of everything that you've done and then hand it off to management so that they have it for future reference. Our scenarios for troubleshooting are a little bit more detailed than the normal scenarios that we get. So in the first scenario, we have identifying a connectivity issue. And the problem is that the user reports that they can't access the internet. So the first part of the solution would be to verify that the physical connection is all good. So their wires are all set up, their routers are fine, that part's fine. So that would be layer 1. The next layer would be to test the IP configuration because it's on layer 3, and that has everything to do with being able to access the internet, because on the local network is layer 2. So on the data link layer, you're interacting with everybody that's inside of your same network. On layer 3 is when you actually start communicating with the internet at large. So we need to first verify physical, and then we test the stuff on layer 3 because that's actually routing and the internet. So then we would use things like ifconfig or ipconfig to see what the IP configuration of that machine is, and then you can identify a DNS misconfiguration as the root cause and fix it in this particular case, we're just assuming that there was a DNS misconfiguration, and that's what it came down to. So ipconfig is something that's on Microsoft machines, Windows machines. ifconfig is something that is on Linux or Unix-based machines, but it essentially does the same thing, where it shows you what the IP configurations are. It shows you what the subnet mask that your machine is assigned to. It shows you IPv4, IPv6 addresses. It shows you the MAC addresses, all of those things that are necessary for that specific machine that you're on. And then based on that, you can see how your IP has been configured. If you don't have the right subnet mask or something, whatever the issue might be that is preventing you from accessing the internet. The next scenario would be to resolve a latency in an application. So latency has to do with the speed of the delivery, right? So the problem is that a business critical application is running slowly. It's not fast enough. So the solution would be to, number one, use a packet analyzer to identify congestion at the transport layer. So if it's running slowly, if it's an application that's actually running slowly, that means transportation. The transport layer is slow. There's something going on that layer for transport layer that has to do with TCP and UDP and all of those protocols. So once you understand that, the datagrams and the segments of the data that's transferring or transporting on that layer, once you identify that congestion, then you can optimize the traffic flow by adjusting the quality of service settings, and then you would be able to optimize how traffic flows according to the individual protocol. So if it's a datagram or a segment, so segment belongs to the TCP protocol, datagram belongs to the user datagram protocol. So depending on what protocol it's actually using, and then depending on the ports that are supposed to be running and the subnets and all of that, depending on all of that stuff, you would adjust the quality of the service so that you can actually optimize the flow of the traffic. Scenario 3 would be mitigating a firewall misconfiguration. So the problem is that users can't access an internal resource. So then you need to first check layer 4 and layer 7 configurations for blocked ports or incorrect rules. So layer 4 again is the transport layer, and the transport layer has to do with whether or not people can use the TCP, UDP protocols, whatever it is, to be able to access certain internal resources. Even though it's internal, they may need to access it via the network connection, right? So there's some kind of an issue with the connection. And so first we check layer 4 to make sure all that's good. And then layer 7 is the actual application layer to see if there are any ports that are blocked or there are incorrect rules that have been set on the firewall rules that are blocking people for their individual ports, or they're blocking certain applications for being able to access those internal resources. And if that's the case, you make the proper configurations and then you adjust the firewall rules so that you can restore access for these users that can't access. And it says users, right? So it's not saying a user, it's saying users. So it means that there's a group of people, whether they're in the same office or across the country, whatever it is, there's a group of people that can't access this thing, which means that there is a specific rule that is either applied to an individual protocol or a port, or it's applied to an application that all of these people are using, and those protocols or ports or applications are being denied access to this internal resource. And then once we've identified that, we would adjust the firewall rules to restore that access. Scenario 4 would be isolating a routing issue, and the problem is when there's traffic between two sites that is disrupted. So two sites could be physical locations, right? So you have, especially if it's considered a routing issue, it's most likely two physical locations that can't access each other. So you have one LAN for one location, a local area network in one location, and then you have another local area network in another separate, completely physical, separate location, and they can't access each other. They can't, the traffic between those two sites is disrupted. So the first solution, the first step is to use traceroute to pinpoint where the route is failing. So at what point between these two sites is the packet being dropped? Are we experiencing packet loss? And then you would reconfigure those routing tables to be able to restore the connectivity between these two sites. And the final scenario would be documenting a DNS failure. So multiple users report that they can't access websites. They have a DNS issue. They can't access domain names. That's essentially what a website is. It's a domain name, right? So First, we want to verify the DNS server's availability and then update the DNS record. So we just want to make sure the DNS server is actually up and it's running. And if it is up and it's running, then we need to update our DNS records for, I don't know if it's an IP address misconfiguration that happened, or the cache, the host's cache, the host list, or the DNS resolve, or the resolve on system D. It could be a variety of different things that we need to update our DNS records for, to just make sure that these people can actually access those things. And as you get the error, right, so you get a report, you document it. You verify the DNS availability, you document that. You update DNS records, you document that. You document everything that you've done to resolve the issue for future reference. So documentation happens at every step. You get a report, it's documented, and it's usually done with some kind of a ticketing system. And then from that, you start adding notes to that ticket that's been assigned, and you update the status of it. You know, it's been acknowledged, we're working on it, it's in progress, it's been resolved. And once it's been resolved, it gets added to the archive, so that in case we need to refer back to it, we can. And then we back up all of those archives, because we don't want to lose that data. Documentation is very, very important. I feel like it's one of the probably the only few log types that you wouldn't delete ever, because you want to have a stockpile. You want to have an entire vault of everything that you have overcome in the past, so that you know what potentially can be done, what has happened, if we've ever encountered this before, what did we do before, was it the same people that attacked us, you know what I mean? There's so many different reasons why we would want to keep our troubleshooting documentation. We want to keep that for as long as humanly possible. So maybe it won't be on hot storage that's available right on the computer that we're working with, but it should be at least warm storage, so that we can refer back to it regularly, so we can see what we did in the past, if it was successful, if we should just do it again, or if we need to update the approach that we took, etc. Okay, time for some practice questions. So troubleshooting methodology. What is the first step in the troubleshooting process? You want to identify it, right? That's basically it. So it's like, identify the problem. That's the first step. Establish a theory would probably be the second step. I think it is the second step. Test the theory would be the third step. Document the resolution would be the last step. So the first one is to identify the problem. Which action is part of identifying the problem? Reproducing the issue to verify its existence. That's not the one. Testing network configuration for errors, implementing a rollback plan, updating firewall rules. So the closest thing to identifying the problem would be the testing of the network configuration for errors. Reproducing the issue to verify its existence. I think it would be part of like isolation. And then implementing a rollback plan is when you are going in resolution and trying to resolve something. Updating the firewall rules is also a part of resolving something. I would say testing the network configuration, but reproducing, I think, would be an answer as well. So, okay, reproducing the issue to verify its existence would be a part of identifying the problem. Which tool would you use to test network connectivity between devices during troubleshooting? So the network connectivity, right? So SSH is for remote connection. So this is not really a tool that we would use for troubleshooting. It's usually a tool that we would use for administration, for trying to manage something. Simple network mapper protocol could be something that we would use for network connectivity. Wireshark is between devices during troubleshooting. I feel like Wireshark could, Traceroute, Wireshark, and SNMP, all three of these have a purpose for network connectivity troubleshooting. If we're doing it between devices during that phase, I would say it's between the Traceroute and the SNMP protocol. And if I were to commit myself to an answer, I would say it's Traceroute. Cool. All right, it is Traceroute. That's awesome. What is the purpose of a rollback plan in troubleshooting? So this is our contingency plan, right? Just in case our resolution doesn't go as planned, we want to have a fallback that we can roll back to. So to collect information, no. To define network documentation, no. To revert changes if the resolution causes additional issues, yes. After resolving an issue, what is the next critical step in the troubleshooting process? You've already resolved it, right? So if you've resolved the issue, the very next step is to document everything. So verify full system functionality So verifying the resolution would probably actually be the very next step. And documentation should be happening throughout the whole process. So I stand corrected on that. But you don't want to close all network connections. You don't want to reassign IP addresses. You don't want to escalate it to a higher level support, because first you've resolved it, which means the escalation and all of that stuff would have already been done. So you just want to verify the system is actually functional. Which layer of the OSI model should you check first when addressing a physical connectivity issue? And that would be the layer 1, physical, right? Layer 3 is network, layer 4 is transport, layer 7 is application. So the further that we go from layer 1, the further we go from the physical layer. So if you're addressing something on the physical connectivity, you want to obviously look at layer 1, which is the physical layer. What should be documented after completing the troubleshooting process, and the tools used during troubleshooting, root cause, steps taken, resolution, total downtime, usernames of affected users. I think it should be all of these, just to be clear. All of these things should actually be documented for the troubleshooting process. But the answer that seems to be most comprehensive would be root cause, steps taken, and resolution. Which best describes a systematic troubleshooting approach? So testing random solutions on, no, that's not the answer. Following a structured process to diagnose and resolve. That's pretty systematic. Yes. Replacing all hardware components. No. Escalating all issues to a higher level. No. So replacing all hardware components to rule out faults sounds like overkill, especially if you don't think it's a hardware issue, or if it ends up not being a hardware issue. That's kind of silly. Escalating all issues to a higher level support immediately also is you not doing your job. So you need to do as best of a job as you can before you escalate it. If you're out of your depth, you would escalate it. Testing random solutions, just the word random is like, that's not the answer. So following a structured process to diagnose and resolve, that is systematic. If a trace route test reveals packet loss at a specific hop, what is the likely issue? DNS misconfiguration, routing problem, issue at the end of the user's device, a failure in encryption. This is not an encryption issue. This is also not a DNS issue. It is a routing issue. An issue with the end user's device is also not a portion of this, because we're talking about packet loss at a specific hop. What traceroute does is it traces the route that a packet takes to go from your location to the destination, and it takes several hops to get there. So it'll go from your router to another router to another router. It'll go probably to your internet service provider's router, and then from there it'll go to another router until it finally lands at its destination. So this is a routing problem that is at that specific hop that the packet loss is occurring. What is a key advantage of documenting resolved issues? It ensures faster diagnosis of similar problems in the future. That's why we want to document. Yes. It prevents the need for further updates to the system. That's not true. It eliminates the need for monitoring. That's not true. It automatically fixes recurring. That's also not true. So the only answer is A. And that's it. That was really quick. So now we can actually move on to cabling and interface issues. So now we've covered the methodology of what we would do for troubleshooting. Now we're going to look at a specific type of troubleshooting, which is cabling and interface, and obviously we'll have other types of troubleshooting that we will be doing as well. This one is going to have to do with cabling and interface issues. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. So cabling and interface issues are, I would say they're one of the, or the set of the more common issues that happen, because cables are actually so flimsy and they can weather quickly, and something can drop on them and they could get cut in half without you actually noticing. Especially if it's a fiber type of a cable where it has a very thin plastic inside of it as the transmitter, or if it has glass inside of it as the transmitter of the lights that are supposed to give you your signal. So cables can be quite flimsy or sensitive or delicate, so to speak, and anything can happen that could ruin them or harm them. But then there's the other issue where they can actually, there's something called crosstalk that we'll talk about in a little bit, that actually happens from the electromagnetic field or the electromagnetic emissions that come from these cables that could actually affect the communication that they can potentially have with each other. And there's just a variety of different things that can go wrong with cables. And the same thing with interfaces. So the cabling and interface issues can significantly affect the network performance, the reliability of the network, the connectivity of the network, and things like crosstalk or attenuation, which is a very fancy word. I like that word for whatever reason. And then mismatched transceivers are common in network environments, and these are some of the things that we're going to be talking about in this particular section. And just understanding these issues and their mitigation techniques is very essential for ensuring optimal network functionality. And this goes into the physical layer of your network, right? So cabling, the actual physical cables and the physical transceivers that connect your various devices and allow for the transmission of data back and forth, all of those things fall under the physical infrastructure of your network. And to just make sure that this layer is taken care of and it's all good will save you a lot of headaches down the line when you're trying to troubleshoot something. So as we looked at some of the pictures of like the horror stories of the craziness of what a server room can look like if it hasn't been organized properly, and all of those things can, if you avoid them, if you actually do organize your server room and your network room and your wires, if all of those things are done really well, then it'll save you headaches, it'll make troubleshooting easier, and for the most part you can rest assured that the physical connectivity and the physical cabling and the devices themselves are not the issue, and it's something logical that you need to just go and fix through your configurations or the setup and the configuration. I think configuration is probably the best word to use for it. So let's talk about these cabling and interface issues, and then what we can do to resolve the issues for these types of problems. First, we need to talk about the cabling problem. So the common cabling problem number one is crosstalk. And this occurs when electromagnetic interference, so EMI, from one cable disrupts the signal in another cable. So there's the near end crosstalk, also known as NEXT, very cool acronym. And this is the interference at the same end of the cable where the signal originates, right? So it's happening on the same section where the signal is starting, where the signal is originating. And so this is near the end of the connection that the signal is originating from. So this is where the signal is coming from, and the interference is happening at the origination, at the point of origination. Point of origin, that's a good word, for the signal itself, right? So near end is the next, which is the interference that happens where the signal originates. Far end, also known as fexed, is interference that happens at the opposite end of the cable, the opposite end from where it originates, so where the signal ends up at and where it goes to, right? So signal originates somewhere, and from where it's originating, that would be the near end to the origination point, the point of origin, and then the far end is the furthest point from that point of origin, right? So you have two types of crosstalk, and next or fexed. Now, the causes would be poor cable shielding or insufficient twisting in twisted pair cables, or running cables too close to the high EMI devices or to other cables, right? So, and it could be there's just too many cables that are jumbled together, so the signals from all of these cables are messing with each other, or you haven't put enough space between, device number 1 and device number 2, so they're sitting right on top of each other. Therefore, the point of origin, right, where the signal is originating, is way too close to each other, and the strength of those devices, the electromagnetic fields, the signals that are coming from those devices, they're so close to each other that they are now crossing over and they're contaminating the signals from each other. Therefore, it actually runs through the cables and it messes with your overall connection. So the mitigation would be to use high quality cables, number one, so Cat6 or Cat8 with better shielding or tighter twists if you're going to use twisted pair cables. So use just higher quality cables. It's more expensive, obviously, to do this, but it saves you headaches down the line. It saves you time and energy and money for troubleshooting down the line if you actually just use the higher quality cables like Cat8, right? Then maintain proper spacing between the cables and the EMI sources. So when you actually are putting your devices, if you're using the same rack to house multiple devices, make sure you at least have one unit, right? The rack unit that we were talking about, which is 1.75 inches, right? So each unit is 1.75 inches. So have at least one rack unit of separation between the devices, which will then provide, let's say, 2 rack units of separation between the actual ports that the wires are connected to. So definitely have proper spacing between the devices themselves, the EMI sources, and then of course the cables themselves, and just make sure that it's not too congested and it's like cross cable, and just the images. Just refer back to the images that we were looking at when we were looking at physical infrastructure. Just my mind literally breaks when I think about those images. You don't want to have something like that. You want to have nice organization. You want to have short cables for the points where their devices are supposed to connect to each other, as we looked at those images. And to just, I feel like it's a good idea to just look at those images again, just as a reminder reference, because telling you to go back just in case you skipped to this portion of the training, I don't want to send you back to another video. So I'm just going to show you the image real quick. So this is just kind of an example before and after image here that we can use for the purposes of this crosstalk conversation and pretty much everything else when it comes down to trying to avoid cabling issues or interface issues. So as you can see on the left hand side, this is very disorganized. The power cable is running right down the middle, and it looks like there's other cables that are actually connected to the same little Velcro strap that has the power cable. So these blue cables that are going to these servers, it seems to be they're actually connected to the power cables themselves. They're not connected to the power cable, but they're like bundled up in the same bundle that has the power cable. So that's a little bit of an issue. And then we have the power source right here. So this thing with the large power cable, it's actually at the bottom right here. And what has happened here is that they took this off of the rack and they put it at the very top so that that power cable can first be moved towards the top and just easily hangs over. It doesn't interfere with the rest of the wiring here. And then they've organized a few of the other elements of this to actually make sure that these wires are, number one, the wires are actually shorter. And the second part is that these little these boxes that you see right here are actually housing the longer portions of the wire. So let's say you're not even using shorter wires and you're just still using the same wires, but what they're doing is that they're at least wrapping up those extended portions, these extra portions of the wire, and they're putting it inside of these boxes that you see right here to help with the organization and to keep them in their own segment so that they don't cross-contaminate with the wires on this particular section. And the devices themselves have been fully separated, and it's obviously way more visually pleasing. But because of the fact that these wires literally are all cross-contaminating, they're all crossing over to each other, and you can't tell what the hell is going on, and you don't know what's being connected to what. That's one big issue. The second issue is that there's heat that's being generated from all of these things that is now affecting the rest of the wires, and the more they are contaminated, the more they're tangled up. The more that they're tangled up like this, the more heat generates. So when you separate the wires, the energy that's passing through these wires also separates, so the heat itself does not contaminate the sources of the signals or the actual signal strength. And then of course it makes it a little bit nicer and makes it easier to manage and organize. And of course the electromagnetic emissions are also under control, and they're not as crazy because again the wires are not tangled up together and messing each other up. And so we see over here, it seems to be that these portions that we see right here have also been changed. So the switch and the router that are down here seems to be that they've been reorganized. You can't even see them over here. Or actually, no, we see this has been placed right here. I can't see where the router has been placed. I think the router has been placed right above here. So that's probably the router itself. This switch that we see right here, this main switch, is the switch that has been placed at the top right here. And it's a simple example. This is not a large server room or a network room in any way, but it's just, you can see a really good before and after example of what it will look like when you organize your wires. And then there's just so many extra benefits that comes from organization like this, apart from just the fact that it's nicer to look at and it's easier to pinpoint where the connections are. There is the heating aspect of it, and there's the collision or the crosstalk avoidance that comes from also having organized wires like this. Okay, our next cabling problem is attenuation. Now, attenuation refers to the gradual loss of signal strength as the signal travels over any given distance, right? So the signal attenuates, which is it loses its strength as it travels over whatever the distance is. So the cause could be that a long cable runs exceeding the cable's maximum recommended length. So for example, the Ethernet cable has a maximum recommended length of 100 meters, right? And so you have a 300 meter cable that's running from one point to another, and now this is actually exceeding the cable's maximum recommended length. Therefore, because of that prolonged length, the length is technically 3x the length of its maximum recommended, or the maximum recommended length itself. So obviously the signal strength will gradually attenuate because it's just way longer than it's supposed to be, right? The recommended length for Ethernet cables is 100 meters. So if you exceed that and you don't have a switch that connects if it has to be more than 100 meters, maybe you can use either a different type of wire, or maybe you can have an extra switch in the middle that these wires connect to, that it passes that signal on. I don't know, something. You can do something apart from saying, okay, we're gonna connect this Ethernet cable to this other Ethernet cable by using a simple adapter that will allow two Ethernet cables to connect to each other, and we're just gonna run this over 300 meters. And it's like, you're not really helping. You're not doing anything. You're actually hurting your environment even more, because you are asking too much from these devices. You're asking too much from these physical sources that you have, these physical tools and resources that you have. So the use of low quality cables with higher signal loss is another version of this, where you're just using cheap cables that as time passes, they deteriorate and they degrade, or they were just cheaply made with low value raw resources, and therefore the signal of that cable just sucks, right? So it again, kind of going back to the other thing, it's like, it's okay to spend a little bit of extra money to actually get stronger quality cables, because your signal will be better, and then you will avoid troubleshooting down the line. You'll avoid having to replace those wires, and now you spent even more money for replacement wires, and you spent time, and you lost your signal, and you lost your productivity, because now you have to do this freaking replacement and troubleshooting. It's just, there's too many headaches, and you can avoid that by just using good cables at the beginning. The impact of this would be that weak signals lead to slower data rates and increased retransmissions, or just connection failures. The failure just connects. Like, worst case scenario, you're not even connected, right? So weak signals could be a slower data rate, fine, but you could actually lose your connection, and that's just, it literally, business halts. If you rely on the internet, your business stops running because of that. So the mitigation techniques would be to use repeaters, or signal boosters for long runs. So if you're going to need something that exceeds the 100-meter length, then use a repeater, a signal repeater, or a signal booster instead of just an adapter. And an adapter is literally just a little piece of machinery. It's not even machinery. It's literally, I'm going to show you what an adapter looks like. And it's literally, it has no other purpose than to just connect two wires together, and the signal just extends from these two wires to the next one. It does nothing to amplify that signal or to repeat the signal strength or boost this. It does nothing. It literally just connects one wire to another one. And you've seen these before, these like adapters, you've seen them all over the place. So it's not something that would be new to you. It's just that it has no purpose other than connecting two wires. So instead of doing that, why don't you just buy a repeater or buy a signal booster and then run longer cables so that you actually still have that signal. You can also switch to fiber optic cables for longer distances because that's what they've been designed for, so that you can actually be able to run them longer than 100 meters and still be able to get the signal that you need. And then you can ensure that cables meet the required specifications. So a Cat6 cable is for gigabit Ethernet, right? So don't use it for anything other than that, right? So make sure that your cables actually meet your required specifications. So if you need gigabit Ethernet, you use the Cat6, right? You don't use anything smaller than that or older than that or less capable to be able to access gigabit Ethernet, because most likely you will probably experience something called attenuation. So let me just show you what these adapters are that I'm referring to, and then we'll move on to the next one. And these are the adapters. There's literally, this is probably the best one that I can think of. It literally just connects two Ethernet cables to help you extend your connection length, right? The actual physical length that your wires can run across. But it does nothing to amplify the signal. So a repeater will actually help you send that same signal strength down the other location because it actually helps to amplify the signal. A booster, right? The booster that we were talking about, where do we have signal booster? These things that we're talking about, these are the things that will actually help you maintain that signal strength over a longer distance than 100 meters. But an adapter, all it does is it literally just connects two Ethernet cables together, and it literally does nothing else. It's also known as a coupler, right? So it does nothing else other than to just connect these various wires together. And they're extremely cheap, which is probably one of the reasons why people use them. But for the most part, they're not designed for big buildings. If you're trying to establish connection across a really large environment or a really big building, then you need something like a signal booster or a repeater. But otherwise, you're going to experience attenuation and you're actually going to lose your signal strength. So you can do something like a signal booster, which we can see right here. And this is an actual device, right? This is and then I'll even go as far as doing this. So if we do an Ethernet signal booster, then you can see that this is an actual device. It looks like a mini switch, literally. And it's designed to connect the two Ethernet cables, yes, but it acts as a middle ground. It acts as this middle point to make sure that your signal doesn't attenuate as it goes long distances. So you have this switch right here. This is a 100-meter cable. It connects to the signal booster, and then it'll go to the wireless access point, for example, right? So this is it's just important to understand this. And these are our power supplies that are controlled for this thing. And then you have the power supplies for each one of these devices over here. And again, this is a 100-meter wire. So it seems like a very short wire, but this is a 100-meter wire, Ethernet wire, that goes from the switch and it's going to the signal booster. And then from the signal booster, it's going another 100-meter wire and it's going to the wireless access point. So technically you have over 200 meters, over 328 feet, or over, 656 feet. You have over 656 feet of distance between this switch and this wireless access point, or 200 meters. That's probably easier to say. So you have over 200 meters of distance between these two different devices, but you're not going to lose the signal. You're not going to experience attenuation because you're actually using a signal booster. So this is what's very important to understand about this specific concept. You don't want to use an adapter. An adapter is not going to allow you to still maintain your signal strength. That's basically the point that I'm trying to drive home here. we have another cabling issue here, which is the mismatched transceiver. Now, a transceiver is this device right here. So it's an electronic device that combines both a transmitter and a receiver into a single unit, hence the name transceiver. And it allows to send and receive signals simultaneously. It's like a radio communication system where it can both transmit and receive radio waves using an antenna. Essentially, it's a device that can both send and receive data over a communication channel. This is what a transceiver looks like. So it's kind of like an Ethernet port. This one, like I believe this one actually allows you to connect an Ethernet device over here. This would then connect to another device, or it's usually inside of a device. So for example, this would be inside of a laptop, let's say, or this would be inside of the switch or inside of the router. You just only see the port right here where the wire gets connected to, right? So these are the ports where the wires actually get connected to, and this other piece that you see right here is inside whatever the device is. So let's say the switch or the router or the laptop, okay? So this is what the transceiver is. Now, when you have a mismatched transceiver, this occurs when incompatible modules are used and preventing proper communication between these devices. So, for example, using a small form factor pluggable transceiver, so an SFP transceiver that is incompatible with the switch or the cable that you're trying to use, or you have mismatched fiber types, so a single mode fiber or a multi-mode fiber. So a single mode is designed for longer distances, multi-mode is designed for shorter distances. So you have mismatched fiber types, therefore your cabling or your transceivers are now not able to connect your actual fiber wires, right? So for each type of fiber wire, so for example, a single mode fiber wire will have a different, I guess you can call it an adapter, or like the end point of the wire will look a little bit different, and it will fit a different type of transceiver than the multi-mode would. And so in that case, you would need to have the proper transceiver that would actually fit the multi-mode fiber wire or the single mode fiber wire. So these are the issues where it's like it's mostly like a formatting or a configuration type of an issue. It's just happening with a physical device and a physical wire. So you are just using the incorrect transceiver to match the type of wire that you want to use, or to match the type of device that you want to use. So when you do this, or if this actually happens, you have a loss of connectivity for the most part, or degraded performance, or you won't be able to actually configure your machines and connect them to each other because, again, the wires don't match the actual transceivers, or the devices aren't able to communicate or connect with each other. So first you want to verify compatibility between your transceivers, between your cables, and your switches before you deploy anything. You just want to make sure that they can connect to each other, that the wires and cables themselves can actually connect these different devices together, so you don't even have this issue. And before you receive them, to set them up, like you just want to do a quick little Google search and find compatible devices for such and such switch and the necessary cables, so you don't even run across this kind of an issue. This is a very silly issue to run across, because you can just avoid it by just doing some decent research before you even before you even order your cables and your devices and things like that. So that's kind of the main reason why something like this would happen, is that somebody didn't think about the order, or they didn't research the order in advance, or I don't know, they were trying to save money, so they ordered like aftermarket type cabling, or they ordered from. It's just research. Like for me, it feels like it's very common sense, and you can avoid this particular issue with just doing some proper research, so that you just know before you place the order, you know what cables and transceivers and switches and all these things, which ones are actually compatible with each other, and then you just order the devices that are compatible and they can connect to each other. That's kind of the only thing that I can think about. And then you match fiber transceivers with the correct type of fiber optic cable. It's so simple, right? So if you have a fiber optic cable, which is a single mode fiber optic cable, and you want to make sure that it actually connects to your device to actually give you the type of connection that you need, you just need to make sure that the transceiver for that fiber optic cable matches the fiber optic cable that you're trying to connect to. It's so simple. It's like, it's not rocket science. This is very, very simple. Just do some research. Hey, for this type of fiber wire, for this, model and brand of fiber wire, what type of transceiver do I need? Okay, great. I'm just going to order this one. And usually in the description of the transceiver on the buy page, or even in the title of the transceiver, it'll say compatible with these types of wires. And it's like, okay, great. And then we can move on from this. It's not a complicated issue to solve. This one is like a gimme. I feel like nobody should have a problem with this if you just do enough research. All right, so now let's talk about diagnosing these issues and the tools and techniques that will allow us to do this. So there's something called a cable tester. Now, the cable tester comes from different brands and different companies. This is the one that is this specific company that creates this one. It is, Fluke Networks. The Fluke Networks series of devices, they have essentially devices for everything in networking. And they are, I would say, the industry standard. They're like the most famous name when it comes down to networking devices, specifically for testing devices and setup and things like that. We're not talking about like switches. I'm pretty sure they probably offer switches and things like that as well, but this is for actual configurations and troubleshooting and the management of the network. So this specific cable tester, so in general, first of all, cable testers detect issues like crosstalk or split pairs or open short circuits on the cable. They'll measure the cable length and verify compliance with the standards. Some of them will even tell you, hey, the error seems to be at, foot 45 of this cable. So from where you've connected this to, from when you connect the cable to this actual cable tester, it'll say, yeah, measure out 45 feet. And at foot 45 is where the split pair takes place, or there's some kind of a short circuit on this wire. So this is the power of these devices. It's very amazing, actually. This specific device, this little device that you see right here, which is probably small enough to fit inside the palm of somebody's hand, costs $5,372. This is not a cheap device, okay? None of their devices are cheap. I don't think I've seen a single device that goes under $1,000. I feel like this was actually one of the more modestly priced devices that I saw on here, and it just so happens to be that it's a cable tester. And Fluke Networks, I mean, they're amazing. They're the industry standard, but these things don't run cheap. This is not something that, unless you really have deep pockets, this is not something that you would buy for yourself. This is something that your employer would provide to you. This tool is called the Time Domain Reflectometer, the TDR reflectometer. I feel like that's how you pronounce that. This identifies faults along copper cables, including the breaks in the cables or any kind of attenuation point where your signal is slowing down or you're losing signal. But this is specific to copper cables, and this is a Megger brand. I'm just mispronouncing everything now. And this seems to be a little bit more, like the interface for this seems to be a little bit more informational, and there's obviously more options and things like that. But it is for the older types of cables. I don't think there are, the new era of cables, the modern cables are going into fiber, and instead of copper, they use glass and plastic, specialized plastic. So you will still run across copper cables because depending on the resources of the company or depending on their goals or whatever they're trying to do, they will probably still use copper cables. So this is not something that is fully outdated and you're just not going to run across. If they're mentioning it inside the most recent version of Network Plus, that means this is still in circulation and we're still going to end up using this. I don't have a price point for this for you. You are more than welcome to research it and maybe drop a comment below and let me know how much the TDR tool from Megger cost, the TDR 2010. Let us know how much this thing costs, but I can't imagine that this would be cheap either. It doesn't look cheap in any way. So this specifically identifies faults along copper cables, and those faults could be a break in the cable or the attenuation point of the cable. Now, this pretty little device right here is the Optical Time Domain Reflectometer, so the OTDR, and as the first word implies, this is for fiber optic cables. So it essentially locates faults and measures attenuation in fiber cables specifically. And this just looks fancy. This just looks like a really modern, cool type of a device. And it even has this is like a handle that you can easily grab with one hand and walk around and do all these things. And then the screen, it just looks so freaking cool. This looks like a futuristic device. But basically it does the same thing as the Meta device that we just saw before, but except looking at copper wires, instead of looking at copper wires, this looks at fault and attenuation for fiber optic cable. So the optical time domain reflectometer. For these last couple ones, I don't have any images for you, but you can always just Google the images for this. The loopback tester verifies the interface of the device by looping the transmitted signal back to the receiver, just so you can see what the interface of the device is actually like, what the signal itself would be like, and the speed of the loopback might be like, if it actually transmits the signal without any kind of dropped or slowing down attenuation in any way. So that's a loopback tester. We have the network monitoring tool. So this actually detects errors like packet loss or high latency that is caused by cabling issues. So this actually helps you monitor the network itself, but it actually is looking at the physical infrastructure of the network, because we do have network monitoring tools that are software based and they're logical, and they look at your network speeds and things like that, and if you experience packet loss and things like that. But in this particular case, we're actually looking at a physical tool that will look at your cabling and then let you know if you have high latency or packet loss based on your cabling issues. So the common symptoms that we will look at here would be if you see these things, for example, you can worry about the interface or cabling being one of the reasons why you're having network connectivity issues. The intermittent connectivity or frequent disconnects, that would be something that would be a common symptom of cabling or interface, right? So intermittent, think about intermittent fasting if you've never thought about it before, if you've never heard that phrase before. Intermittent fasting is like partial fasting. So you fast for a portion of your day and then you eat for the remainder part of your day. So if you have intermittent connectivity, that means you have signal for a couple of hours, and then you have no signal for 30 minutes, and then you have signal again, and then you have no signal, or you have signal for a couple of minutes, and then you lose signal for 10 seconds. This actually happened to me last month or something like that, when I was actually trying to record a video, and I kept having issues with my internet connection, and I was like, what the hell is going on? And all I had to do was I needed to restart my router and my modem and just disconnect all the cables and reconnect all the cables. And thankfully, that was it. But that was actually a cabling issue. It had nothing to do with my laptop, had nothing to do with my Wi-Fi adapter, none of that stuff. It was simply a cabling issue that kept giving me intermittent connectivity. And then the frequent disconnects, same thing, right? These things kind of go hand in hand. If you have intermittent connectivity, that means you're having a lot of disconnects for your connection. Reduced network speeds or degraded performance, that could be something else. This could also be a sign that there's malware installed on your computer or on your devices, but this is a common symptom that could also point to, okay, there might be some kind of a cabling issue. And then we have error messages indicating there are mismatches in your interface. And that by itself is like, okay, well, this is towards the beginning when you're actually setting things up, where as you're trying to set up the network devices, you would get an error message saying, hey, there's an interface that's mismatching, right? The transceiver that you're using, it doesn't work. The wire that you're trying to connect to that transceiver isn't giving the proper signal, whatever it is. So there's some kind of a mismatch in your interface. So this usually would happen when you're first trying to set something up. This shouldn't be something that shows up later on after the network has been running smoothly for several months. Or at least in my opinion, I don't think this would show up after it's been running smoothly. It's usually when you're first connecting something and you're trying to make sure that you have all your connection, then you would get, hey, there's a mismatch for your interface or your cabling or your transceiver, etc. Of course, just like with everything else, there are best practices for preventing cabling issues. And the very first one is to just follow the standards that are set for cabling. So adhere to the TIA or EIA 568 standards. If you don't know what this means, I mean, let's actually just Google it just to give it to you, because I don't want you to have an excuse for not being able to say, okay, no, I didn't know what this was, and then you don't take the time to actually go research it. So we're literally going to do it together. So the TIA EIA 568 is the set of standards for telecommunication cabling in commercial buildings. So the Telecommunication Industry Association, which is TIA, publishes the standards, which are accredited by the American National American National Standards Institute, which is ANSI. So what these things do, they help plan and install structured cabling systems, establish minimum requirements for cabling categories. They determine the order of wires in RJ45 connectors. The different parts would be TIA EIA 568.0D, which specifies generic cabling. 568C specifies technical performance criteria for balanced twisted pair. 568.3D specifies technical performance for optical fibers. And so it's just basically the standards for wiring and cabling, okay? And it's developed by the Telecommunications Industry Association. So they tell you, based on the type of wire that you're using, what you should do, what the standards are, and how you should set up your network and your infrastructure so that you have no issues. So you adhere to those standards, and lo and behold, believe it or not, you're not going to have any kind of an issue for your interface, or at the very least, you won't have it for a while, right? So it's not that complicated. Like for the most part, we don't have to reinvent any wheels in the world of IT. There is a standard for everything that you're trying to do. There's a framework for everything that you're trying to do, for all of the tools that you're trying to use. And if you just follow those standards and follow those frameworks, 9 times out of 10, you're not going to have any kind of problems. And that 10th out of 10 time will most likely be some kind of an anomaly type of a situation where with enough research, you'll be able to figure that whole thing out. But as long as you're following the standards, you'll be fine. Label your cables clearly for easy identification. It's so common sense. Like these stuff, they don't need explanation. I don't need to go through an explanation for this. If you don't understand why you should label your cables, there is nothing that I can tell you to help you. Maintain proper cable management. So use cable trays, use ties, use management systems to avoid physical stress on the cables. Keep cables organized and separated by function. So the data cable versus the power cable, label them, separate them, use those Velcro ties to patch them up or bundle them together. Okay, these are not complicated ideas. Match components correctly. So verify compatibility between cables, transceivers, and devices before you order them. That would be the big piece right here. That should be like a big note in bold capital letters. It's like, before you order the cables and the transceivers and the devices, make sure you've done enough research to see that, okay, all of these things actually are compatible with each other. We can rest assured that once they're delivered to us, they will connect and everything will be fine. Use manufacturer-approved components for critical connections. It's, again, super basic. This is not something that requires further explanation. Test after installation, also very basic. Perform post-installation testing to ensure cables and interfaces are working correctly. Log results for future reference and troubleshooting. All of these things are basic common sense. Upgrade to quality components. That's another one, right? Use high-grade cables and transceivers to minimize crosstalk and attenuation, to also minimize headache for further troubleshooting down the line, for having to replace those aging cables sooner than later, right? So if you use high-grade stuff, you won't have to replace them. They won't age as quickly. And if they do age, then replace them proactively to prevent performance degradation. You should be very similar to what we do in cybersecurity, where we do vulnerability scans regularly and we do scheduled vulnerability scans. You should be doing the same thing. You should be testing your cables regularly based on just scheduled tests, not because there's some kind of an issue with connection in your network, because it's a good practice to just look at everything and keep track of everything and be like, okay, this looks great. And, oh, you know what? This one kind of looks like it's degrading. Let me go ahead and order a replacement now, and then we'll replace this so that we don't experience any kind of performance degradation, attenuation, none of that stuff. We're just going to replace it in advance, and everything is going to be fine. We're not even going to have an issue, right? That's a part of the scheduled audit, the scheduled testing of your devices and your cables and your transceivers to just avoid a problem. Which brings us to our scenarios. So Scenario 1, resolving the crosstalk in the office environment. The problem is that employees report frequent network slowdowns. So we want to upgrade to shielded Cat6a cables and reroute them away from high electromagnetic field devices, electromagnetic emission devices. So upgrade to shielded cables, meaning get higher quality cables, and then reroute them away from these high EMI devices so there is no crosstalk potential even. Scenario 2 would be addressing attenuation in a warehouse. So it's a big situation, right? It's a big location. Attenuation means that you lose your signal power over long distances based on the wire. So the problem would that be that network connectivity drops frequently at far ends of the warehouse. So we would install Ethernet repeaters and then replace the long copper runs with fiber optic cables. There you go. And then just make sure, of course, that they are actually compatible with each other before you order them, and then find out that they are not compatible, and now you have to reorder and refund and return and all of that stuff. Scenario 3 would be fixing mismatched transceivers. So the problem is that a newly installed switch fails to connect with its uplink. Notice that it's a installed problem, right? It's an installation problem. So you would replace the multi-mode transceiver with a single mode transceiver compatible with the fiber optic cable, because you need to check and research about compatibility so that you know that these things are actually going to be able to connect to each other. This is not a complicated concept. You do your research in advance, and this is not even going to be a problem, right? It's an installation issue, right? So whoever ordered those things in the first place should be, I don't know if they should be fired, but somebody needs to talk to that person. Scenario 4, diagnosing signal loss in fiber optic cables. The problem is that a branch office experiences slow network speeds. So we would use an optic, whatever the freaking name of the device was, I already forgot. Some kind of metrometer, whatever. I know that it's a device that measures it tests the wires to identify a bend in the fiber optic cable causing attenuation, and then replace the damaged section of your fiber optic cables. I need to remember what this thing stands for. I just know that the first word was optic, or optical. Maybe that's what the first word was. But this is definitely that device, that fancy looking device that we looked at, that allowed us to test our fiber optic cables. Scenario 5, ensuring proper cable installation in the data center. The problem is that patched cables or patch cables are tangled, making troubleshooting difficult. So we would implement a cable management system with labeled and color-coded cables. Oh my God. Who would have thought that organization would actually save our ass in the long run? Unbelievable. And that's it. I think we are now going to go to our practice questions. And here we go. So what is crosstalk in network cabling? A loss of signal strength over long distances. That would be attenuation. Interference caused by signals from adjacent cables. That's pretty good. A mismatch between transceivers and cables. That is a transceiver mismatch. The inability to maintain a secure connection. That is some kind of it's like a cabling or wiring issue. So what do we have? We have the interference caused by signals from adjacent cables. Which type of crosstalk occurs at the same end of the cable where the signal originates, right? The point of origination. So we have two. We have either fixed or next. None of these things even matter. So the near end crosstalk is the point closest to the point of origination. The far end is the point that is furthest from that point. So near end crosstalk would be the answer. What is a common cause of attenuation in copper cables? So excessive twisting of pairs within the cable runs exceeding the maximum recommended length, using shielded cables in low EMI environments, mismatched IP addressing. This is irrelevant, has nothing to do with this question. Using shielded cables in low EMI environments would actually be something that we would do to kind of secure the environment or prevent attenuation or prevent signal loss. So that's also not relevant to this question. The cable runs exceeding the maximum recommended length. That would probably be my answer to this. Excessive twisting of pairs within the cable doesn't really seem like a relevant answer either. So I'm going to say B. Okay, cool. What tool can identify faults like breaks and attenuation points in copper cables? Okay, so we have these various tools that can do the same thing. They just deal with different types of cables. So specifically for copper cables, The cable tester can actually do this, but I don't think it's the cable tester. And the optical time domain reflectometer was the one that is for fiber optics. The time domain reflectometer was the one that was dedicated to copper cables. And then the loopback tester, it just tests the signal loop back to the interface. So I would say C is the answer for this, because I believe C is the one that's relevant to copper cables. Okay, great. Which of the following best describes a mismatched transceiver issue? Using a multi-mode transceiver with a single mode fiber cable. Yeah, that's a mismatch for sure. Running cables parallel to power lines. No. Exceeding the maximum length for Ethernet cables, that's attenuation. Poor organization in cable management systems. I mean, it's not a mismatched transceiver issue. So this is the only one. A is the only one that actually addresses this. What is the maximum recommended length for Ethernet cables before signal degradation occurs? And that was 100 meters based on that example that we saw. What is the purpose of a loop back tester? To locate faults in fiber optic cables, that would be the optical reflectometer or whatever. To verify proper functionality of a device interface, I believe that was close. To detect electromagnetic interference, to measure attenuation in copper cables. So it's not A, it's not D, and it's not C. The only thing it would be to verify the functionality of a device interface by actually testing the loop back. Which technique helps reduce crosstalk in network cabling? And so using shielded cables in proper spacing, that's pretty solid. Increasing the length of cable runs is no, that's not it. Avoiding the use of cable testers, that's definitely not it. Disabling unused ports on devices, this is like security hardening. So this has nothing to do with reducing crosstalk. So using shielded cables in proper spacing, that would be the answer. What is the most likely solution for resolving attenuation in a network using copper cables? So you want to resolve the loss of a signal over long distances, right? That's basically what attenuation is, or the slowing down of the strength of the signal, whatever that is. It has to do with the strength of the signal over long distances. So if you're using copper cables, what's the most likely solution for resolving attenuation? So installing repeaters or signal boosters, that's great. Replacing transceivers with high-speed models, not really, it has nothing to do with attenuation. Changing IP addresses of affected devices has nothing to do with this. Increasing cable tension during installation, that is also, it seems like unnecessary. So installing repeaters or signal boosters. Which device is used to identify faults and measure attenuation in fiber optic cables? So we have the optical time domain reflectometer, the OTDR. Reflectometer is the word that I'm trying to remember. So the optical time domain reflectometer has to do with fiber optic cables. And that's it. We have officially wrapped our cabling and interface issues. So now we're going to look at network services and performance issues under our troubleshooting section. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. Troubleshooting network services and performance has more to do with the various protocols that are involved in network interactions and network communications, as well as the software and the digital tools, the logical tools that we would end up using to try to troubleshoot those various problems. So the performance of your network and the services that are used on your network really don't have anything directly to do with the various infrastructure, the physical devices that are on your network. The physical devices allow for the connectivity to actually take place, And then just depending on what you need your network for, there will be a variety of services and protocols and software tools that you would end up using to make those things happen. So the various protocols or the various services that we would need for a network to actually function at the bare minimum, at the basic foundational level, would be things like the dynamic host configuration protocol, the domain name service, the domain name system, routing tables, and all of these things play a very critical role in maintaining seamless communication, meaning just smooth, streamlined communication across all of your devices inside of your network. Misconfigurations in these services can actually disrupt your connectivity, degrade your network performance, completely just throw everything out of whack. It's almost like throwing a monkey wrench, so to speak, inside the gears of a machine, like of a really big machine or something like that. So when you have misconfigurations in your DHCP or your DNS, misconfigurations in DNS could actually stop people's computers from even being able to access a given website, right? So a simple misconfiguration, which sometimes can be a dot that's out of place, right? Or a number that was accidentally typed in, and that could actually stop your domain name service from working properly. So these things are detail oriented, just like with anything else in engineering and performance based stuff. So additionally, performance bottlenecks like the bandwidth constraint or latency or jitter can negatively impact real-time applications, and this requires proactive monitoring and optimization to ensure a smooth network experience. So obviously, these are the things that we're going to be talking about in pretty great detail. And this particular section, I've compiled even more notes because these are the things that I don't want to try to explain out of the top of my own head. I want to give you precise instructions on these things because these are a little bit more nuanced and they're a little bit more detail oriented. So I really just want to make sure that you have the best available notes that are available for you. So let's jump into these various network services, performances, and of course, how to troubleshoot them. First, we need to look at the big category of issues with the actual network services. So the first in this category would be the misconfigured dynamic host configuration protocol. So as the definition, dynamic host configuration protocol, also known as DHCP, is a network service that automates the assignment of essential network settings to devices on a network, and that could be things like the IP address that's assigned to a new device that comes in, the subnet mask for these groups of devices, the default gateway, so the IP address of the router that directs network traffic, and then the DNS server, which is the IP address of the domain name system server that translates domain names like Google into the IP address for Google. Okay, so all of these things are done dynamically or automatically would be another way, because this protocol automates the assignment of all of these network settings. So when a new device enters your network and then it connects to your Wi-Fi, it's the DHCP that assigns the IP address for that, and then it assigns the subnet mask, it assigns the default gateway based on the router that they've connected to, and of course the DNS server that they would end up using. These are the things that are done automatically by the DHCP, the Dynamic Host Configuration Protocol. So this is what the purpose of DHCP is. So now we need to understand what it means for this to actually be misconfigured, which I'm pretty sure you can already guess that essentially any of these things could just be configured incorrectly. So what that means, how to identify it, and then of course how to resolve it, how to mitigate it. So first we need to understand the common problems that would be inside of a DHCP misconfiguration type of an environment. The most common, which is our very first in line, is when there is IP addressing conflict. So this happens when overlapping DHCP scopes, or essentially when two or more DHCP servers assign an IP address from the same range, right? So we talked about the subnet mask earlier and the various ranges of an individual network segment or a subnet. So if you can imagine that you have two or more DHCP servers that are working with the same range, and then they're issuing IP addresses from that same range, which is going to be limited, right? They're eventually going to run out of unique IP addresses. And if you have too many devices, or if you have very many devices that are entering your network and then they're connecting to these various DHCP servers, so essentially not having a dedicated DHCP server for an individual subnet, then what happens is that two or more of these servers think, oh, okay, I have all of these ranges, and they're not keeping track of the addresses that the other one has assigned. So they'll just reassign the IP address to a new device. And then you have an IP address conflict where two devices now, two laptops, for example, two cell phones, they've been assigned the same IP address inside of that network. And then now we have a conflict, and manually assigning the static IP addresses within the DHCP scope is another version of this. The DHCP server misconfiguration, like incorrect scope definitions or lease times, could be another reason. And as we discussed earlier, a lease time is the amount of time that an IP address is assigned to a device. So let's say that this is the guest network, and there's hundreds, if not thousands, of devices that come into this network on a monthly basis. So each of those devices temporarily gets an IP address that's assigned to them, and then that IP address should expire within 30 days, let's say, because it's a guest, right? It's not somebody who's coming in regularly. So as a guest, that IP address that's assigned to them needs to expire so that it can be reassigned to another device that comes in. So if you have a lease time that is longer than 30 days in this particular case, let's say it's a 6-month lease time, then that specific IP address is now assigned to that guest device for 6 months, and it won't expire for 6 months. And then during those 6 months, and of course, if this is the lease time that's configured, what's going to happen is that every other guest device that comes in will also get a 6-month lease, and eventually, real quick, you're going to run out of IP addresses, and then now you don't even have IP addresses that are available anymore because they've been leased to these devices that are never going to come back into your building. So it becomes an issue, right? It becomes a problem such a simple problem where it's like, oh, okay, let's say the person was trying to do 30 days for their lease time, and they accidentally put an extra 0. Now it's from 30 days, it gone up to 300 days, which is pretty much a year. And so it's like, okay, so that's the lease time now. So any guest device that comes in is going to have a 300-day lease time. So that something as simple as that could completely throw your DHCP configurations out of whack, right? So these are just some causes. And then to be able to recognize these things, you need to know what the symptoms are that would potentially point to an IP address conflict being the problem for your DHCP configuration. So the network connectivity issue for some or all of the devices, very, very basic. They can't connect to the network, right? Some of the devices or if all of the devices in your network can't connect, that's obviously a symptom. If it says IP address in use as an error when somebody's trying to connect to the network, or let's say the lease time, right? So if somebody's trying to connect and then their IP address that was assigned to them is now being still leased out, or there's two DHCP servers that are trying to assign the same IP address to a range of devices. So obviously that IP address is already going to be in use. So that's another symptom that will obviously declare that we have some kind of an issue with our host configuration protocol, right? Slow network performance is just another one. Slow network performance is one of these symptoms that can pretty much apply to like everything that's happening within the network. And it's like, okay, well, slow network performance could be a physical network device issue. It could be a cabling issue. It could be a DHCP issue. So this is kind of one of those gimme symptoms. It literally applies to pretty much everything. As we've talked about it, you've heard this concept come up so frequently. So it's not the greatest symptom to try to narrow down why we have this slow network problem and if it actually is a DHCP issue. The IP address in use, that's a great error that really points you to the right direction. And it's like, oh, if it's an IP address that's already in use, that has to do with the services that we have that assign IP addresses. So we need to go and fix that or address that for that specific piece. Network connectivity issue is another one of these kind of like blanket type symptoms that this could technically be DHCP maybe. It could also be a physical hardware or cabling issue. It could also be the firewall or something like that. So there's a variety of different problems that could also give you network connectivity. So the most precise problem that could actually point us to DHCP would be this IP address in use error. And again, all of these things could technically be a symptom, but the most precise, the most sniper kind of a thing, instead of a shotgun approach, it's like the most direct error would be that IP address in use error. Now, our next problem, our next common problem for DHCP configurations or misconfigurations would be that there's an exhausted IP pool. So this means that there is not enough IP addresses available within that DHCP scope, right? So too many devices connected to the network, the leases are not being released properly, or the devices aren't properly shutting down, the leases aren't expiring, whatever that is. And so due to that reason, the IP address pool, the scope of the IP addresses that's available for that subnet has been exhausted. They ran out of IP addresses, right? There are not enough available IP addresses. So a symptom of this could be new devices can't obtain new IP addresses. That's pretty solid. Existing devices may lose their IP addresses and become disconnected. That could also be an issue where it's either some kind of a lease issue or there are too many devices that are connected to the network. So these are again, DHCP misconfiguration problems that arise, and the causes for this. It's a little bit more straightforward. It's a little bit more simple to understand. You just run out of IP addresses in your subnet or in your segment for your DHCP scope. And if you run out of IP addresses, it could be, number one, there's new devices that simply can't connect to it, or their existing devices are losing their IP addresses and becoming disconnected. These are the symptoms that would say, okay, I think we're running out of IP addresses. And then the problem is just there are too many devices, and then the leases aren't being released properly, the devices aren't being shut down, or the expiration time for those leases is too long, something around that. The next major problem that we have is the incorrect gateway, which is the IP address assigned to the router, or the DNS settings, the domain name service settings. And the causes for these problems could be that there's a misconfiguration on the DHCP server's settings, or there's an incorrect configured router. So either of these things could be the cause of having an incorrect gateway or DNS problem. The symptoms to be able to notice this is that the device can't connect, or the device can connect to the network, but it can't access the internet. So it's connected to the network. It says that it's actually connected. It says the network is up, and we actually have an actual green light, or, there's no error for the icon for network connection, right? It says you're actually connected to the network, but you can't access the internet. You actually can't go to a website. It just won't load anything for you. So you're connected, but you can't access the internet. That's a obvious symptom that, okay, there's some kind of an issue with our gateway. Either the gateway isn't connecting to the actual internet, or maybe I have the incorrect gateway IP address, or maybe you can't resolve the domain name, right? So you can't go to google.com, but if you actually use the IP address for Google, then you'd be able to pull that up, it's kind of odd, right? So that means that you can't actually connect to the internet because you're able to connect to Google via its IP address, but you can't use the domain name. You can't access the website by its name. You can't go to Microsoft.com, but you can go to the IP address for Microsoft.com and it'll work. And that's kind of that's one of those obvious things that it's like, oh, this is a domain name thing. This is definitely a DNS thing. And then there's the slow DNS resolution time, which essentially means that it's just taking too long for it to pull up a website by its name. It's taking too long for you to be able to connect to that website. And this could also be, okay, maybe there's some kind of a congestion in our network. This could be an issue with the actual devices that are connecting you to the internet. The slow resolution times or the slow connection times isn't the most precise type of symptom that would lead you to believe that it's one error versus another error. It's usually all-encompassing, right? If it's slow, it's usually all-encompassing. Meaning it covers, a slow connection can be a number of different reasons. It could be a variety of different reasons that would give you that slow connection. But if you have an unable to resolve domain names, right, that's a DNS issue, guaranteed, right? If the device can connect to the network but it can't access the internet, that means that there's something wrong with our router. There's something wrong with the gateway. I can actually connect to the gateway, right? It says that I'm connected, but I can't access the internet. So there's something wrong with the ability of the router to be able to actually connect to the internet. Okay, so now that we know what these various problems are and their symptoms and their causes are, now we need to figure out how to troubleshoot our DHCP configurations. How do we fix it, right? So the first one would be to actually verify the configuration of the DHCP server. So the scope definition. So first we need to understand what the scope is, right? What is the scope of the DHCP server? The reviewing of that settings. So when you look at your DHCP scope settings, includes the starting and ending IP addresses. It includes the subnet mask, and it includes the lease times. So we have to make sure that the scope is correctly defined and it doesn't overlap with other scopes. So if we go back to our subnet portion of this training series where we're looking at an IP address range, right? So if one specific DHCP server is managing, let's say, a given range, right? It's supposed to manage, let's say, 100 IP addresses, and it goes from 0.1 to 0.101, right? That would be the last three numbers for that last octet on the IP address. That's the range assigned to this specific server. If another server that we have also has 0.1 to 0.101 as its scope, as its range, that's an issue because they're going to work with the same 100 IP addresses, and most likely there are going to be overlaps, and they're going to assign the same IP address to different devices. So that range of IP addresses, the starting and ending IP addresses that is assigned to that server, the subnet mask that's assigned to that server, and then the lease time that's assigned to that. All of these things could be parts, they are part of the settings that are for the DHCP server, and those could be issues from the get, right? So it's like, first you want to just verify that the settings for that server are what they are supposed to be. If you have confirmed it and they are exactly what they're supposed to be, then we can talk about the next series of troubleshooting, right? So first we understand what the scope definition for the server is. Then we look at any static IP address reservations within that scope. So is there any of those ranges? So from that 0.1 to 0.101, from that range, has any of those IP addresses actually been statically assigned to something else? Has it been reserved for something else? Because that might be an issue, because if it's been statically assigned, meaning that an administrator manually went and assigned it to something, that means it's not available for dynamic configuration. Therefore, that address is essentially out of the range. That address can't be used because it's manually been statically assigned to something and it won't change. The lease time would be adjusting as we already know what it actually is. We would need to look at what the lease time is and then adjust it as needed to ensure that there's adequate availability of the IP addresses. And then the DNS server, so verifying that the correct DNS server addresses are actually configured on your DHCP server. These are all under the verifying the configuration of the DHCP server. So the very first thing that you want to do before you do any of the other troubleshooting steps is you just want to look at the server settings to see, is the scope correct? Is the subnet mask and the lease time, are they correct? Are there any IP addresses that have been statically reserved for something else? Is the DNS server correct for the configuration for the DHCP server? Are all of these things, have they just been set up correctly? If these are actually set up the way that they're supposed to be, then we can move on to our next troubleshooting step. And that step would be to actually monitor the lease usage. So use the DHCP server management tools to monitor the lease usage and identify any potential issues with the lease and how it's actually being used. Identify the devices with long lease times or those that are not releasing their leases properly to try to figure out, is that why we're having a DHCP configuration issue? Is that why we can't assign new IP addresses dynamically because there are devices that have way too long of a lease time or they're not releasing their leases for whatever reason? Then you would inspect the configurations of the devices. So you would use a tool like ipconfig, which is for Windows, or ifconfig, which is for Linux or Mac, to check the IP address and the subnet and the default gateway and the DNS server for the individual devices to see what they've been assigned to. What subnet mask have you actually been assigned to? What default gateway have you been assigned to? Is that even the default gateway that you're supposed to be assigned to? If it's not, then that's why we have one of the issues, right? Is your DNS server the one that you should be using? The IP address that's been assigned to you, is it a static IP address, right? So all of these things are potential reasons why a device could actually not be configured properly, or why the DHCP configuration for that device isn't working, why DHCP why that specific device, why that specific device is not getting an IP address that is able to access the internet, or why it can't connect to the internet and pull up domain names. These could be actual device issues. It might not have anything to do with your DHCP server or your network. It could simply just be that that device, for whatever reason, has an IP address that is belonging to something else, or it's outside of the range for our network, and now it can't connect and it can't do what it needs to do. So any inconsistency or incorrect settings on the device's configurations would point you to, okay, maybe this is why this device is having an issue. So we start from the very top level, right? Let's just look at our DHCP settings, make sure everything on the DHCP server is fine. Okay, that's great. Let's look at the lease settings. Okay, the leases are fine too. There are no devices that are stuck in their leases or anything like that. So let's look at the actual device that's not connecting. Let's try to figure out why you have an issue, right? Because the network's fine. Our DHCP server is fine. We just need to find out why your device is not connecting. Next would be to check for rogue DHCP servers. So rogue DHCP servers can interfere with the legitimate DHCP server and cause various network issues. And using a network scanning tool to identify and disable any unauthorized DHCP servers is a big deal. It's a sign of some kind of malicious actor. So if there's an actual rogue DHCP server that is inside of your network, that means somebody did something that they should not have been doing, because rogue essentially means that it doesn't belong, right? It's not a part of us. It's not a part of our network. We didn't assign it. It just showed up, right? So if that's the case, that means somebody outside of our IT team, out of our networking team, was the one who configured this, was the one who actually tried to add it to our network. And that is a really big red flag for security. It's like, okay, fine, we need to fix the networking problem that this is causing, but we also need to figure out what the hell just happened. How did this happen? How did we get a rogue DHCP server inside of our network? That's a really big issue. That's a big red flag. Then you analyze your logs, right? So review the DHCP server logs for any error messages or warnings that may indicate configuration problems or other issues. And your server logs usually will point you in a really good direction, because the error messages that show up are great tools, or they're great clues that you can use to try to figure out why you are having your DHCP configuration issues. So how do we mitigate this, right? How do we resolve this? The first would be to regularly review and update your DHCP server configurations. Implement the DHCP snooping to prevent unauthorized DHCP servers from operating on your network or even trying to connect or establish themselves on your network. Implement the DHCP relay agents to forward the DHCP requests and responses across different network segments, and monitor the network traffic and performance to identify any address, or to identify and address any potential issues. So mitigation for, and again, this will be another one of those things that you'll hear very frequently, and this is a common theme, regular review, regular auditing and updating of the configuration of whatever the service is, regular monitoring and of the traffic that goes in and out of that service and the performance of that service. All of these things are a basic element in being a network administrator or just being a solid IT team. You want to do regular checkups. You want to monitor things all the time. Even if you're not having an issue, even if there's everything is working smoothly, you still want to run regular checkups. Whether it's on your logical services and your, the DHCP protocol or the DNS, whether it's on that or whether it's on the physical devices and the cabling and the AC inside of the server room, whatever the assignment is for you, whatever the responsibility is that you have to take care of, you want to monitor that regularly. You want to run tests regularly just to stay ahead of any potential errors that may arise in the next 2 months or something like that. So by carefully configuring and monitoring the DHCP server and addressing any misconfigurations, you can ensure smooth and reliable network operation. Okay, the next problem that we are troubleshooting for our services is our DNS misconfiguration. So the domain name system, also known as DNS, is the internet's phone book, right? So it translates human-readable domain names like google.com into machine-readable IP addresses like the IP address for google.com. And the IP address for google.com changes regularly as a part of their security posture. Just like their certificate authority changes regularly, they will also rotate their IP addresses because they don't want the same IP address to be assigned to this domain name, because there are people that are constantly trying to hack into Google and do penetration testing or whatever it is. And it could be black hat or it could be white hat. Doesn't really matter. To keep all of the attackers on their toes, they will change their IP addresses regularly. So the domain name system is one of those dynamic systems that, as long as it works properly, it will resolve whatever the IP address is for Google anytime that they change their IP address. So all of these things happen behind the scenes without you even knowing it. That's what the domain name system does. So a misconfigured DNS setting can obviously disrupt this translation process, and it leads to significant connectivity and accessibility issues for users and applications and websites and whatever it is that you're trying to do. So it's very simple. It's not a complex kind of a concept to wrap your head around. It basically takes the IP address that is assigned to a domain name, and then it pulls that IP address up for you so that you don't have to remember this, right? You just remember Google, or you remember Gmail, or you remember Facebook, or you remember fill in the blank. You remember whatever the website name is. And then as long as you remember that, the rest of it is done for you by the domain name system, which is very, very convenient. It's very powerful and it's very simple. It's just that it's one of those critical services that if it stops working, now you can't access these websites or these web applications from their names. And you most likely are not going to know what their IP address is. Like, you're not going to remember that. So this is going to be something that is crucial for people to be able to use, to be able to access the internet at large, right? To be able to navigate the internet. Now, the common problems for DNS configuration or misconfiguration, the very first one is just your DNS records are incorrect. So the A record is your IPv4 address. The quad A record is your IPv6 address. So your A record maps the host name to an IPv4 address. So errors in this, so a typo, an incorrect IP address, it prevents the user from actually reaching the intended website. So for Google, if their IPv4 address is mistyped or it's an incorrect IP address, then whoever tries to go to Google won't be able to reach the website. The quad A record maps that same host name to an IPv6 address, and these can hinder access to websites or services that require IPv6 connectivity, which is happening more and more frequently because there is such a limited number of IPv4 addresses available in the internet. The MX record is their mail record. So this specifies the mail exchanger server that's responsible for handling email for a domain name. So the incorrect MX record can cause email delivery problems, such as emails being undeliverable or just bouncing back, right? So that is your MX record, your email record. And then we have the CNAME record, which creates an alias for the canonical host name. So misconfigured CNAME can lead to a redirection loop or some kind of incorrect resolution. And the CNAME could be, google.com could be the normal domain. www.google.com could be a CNAME. So if it has that www at the top of it, that could be one of the versions of it. If you have, lowercase w's and uppercase w's, that could be another CNAME record as well. So there are different versions of this that would end up hopefully just leading to the same actual host name, the same domain name. And every single one of those things, that the capital W's and lowercase w, all those things are considered aliases for the same host name, right? So if this is misconfigured, then you may have an issue with pulling up the website. So if you don't have a CNAME for the www version and somebody actually uses www.google.com, it's not going to pull up the domain name because it doesn't exist. That CNAME record doesn't exist in the configuration. Therefore, if somebody uses that, they won't be able to access the website. The next problem would be the propagation delay. So DNS changes take time to propagate across the global DNS infrastructure. So this can cause intermittent connectivity issues or prevent users from accessing updated resources immediately after changes are made. Now, usually, depending on the hosting service that you use, if you use AWS, even if you use GoDaddy. I used to be in love with GoDaddy, and then I realized that there's, AWS, and AWS servers are just so much faster, and their hosting is so much faster. But even if you use GoDaddy, it still doesn't take that long. It'll maybe take like a couple of hours in the longest, or maybe a day, like depending on what kind of hosting service that you've purchased. But usually, whatever the changes you've made to your DNS configurations, they usually propagate fairly quickly globally, so that people across the world could be able to access your website. So it causes intermittent connectivity, right? This is the big issue with this, is that for a brief period of time, the website will not be accessible because the propagation is taking time, right? There's a delay in the updating of the configuration for that website, so that across the world people can't access it right away. You press submit or you press save on your configuration, and in that moment people have an issue accessing it because it takes a few minutes or a few hours or maybe a day for the changes to actually propagate, for the changes to actually update across the globe. Then there's the DNS server failure. So if the primary and secondary DNS servers for a domain are unavailable due to hardware failures, network outages, security breaches, the devices cannot resolve domain names, leading to widespread connectivity disruptions. For most people, like the majority of websites, this is an issue for their actual hosting service provider. For example, AWS, right? So if you have a server failure, that's on AWS to try to fix that, because you're not the one managing the actual server. Now, if you have an on-site web server, that's completely different. That's on you to fix it. But the majority of companies, the majority of people don't host their own web server. They don't house their own web server in their own building. They're renting one from GoDaddy or from Google or from Amazon or from whatever, just some kind of a service provider. So this is on the actual service provider, the company that's providing the hosting for you. The single point of failure can significantly impact network availability and business operations. And this mainly means that if you only have for your hosting account, you've only chosen one server and then you don't have a redundant server as a part of your plan, that ends up being your single point of failure. That single server that you have because you were trying to save money, that ends up being your point of failure. Because if that server goes down, now your entire website is down. Your entire operation is no longer working. And then this also applies to if you have an on-site server and you only have one server and something happens to that server, now again, your operations have crashed. So the single point of failure concept has a lot to do with your backup servers. It has a lot to do with redundancies. It also has a lot to do with whether or not you have a load balancer that's distributing the traffic that's coming in, and one server is being overloaded and all of a sudden that server crashes and you don't have a load balancer to balance the load, as the name implies, and then send the traffic across multiple servers, or it doesn't have an automatic reassignment that would go from the primary to the secondary DNS server. So DNS server failures, for the most part, are in the hands of the hosting provider. But then there's this option right here that's like, okay, well, as your job as the person that's renting that service from Amazon, your job is to say, okay, well, I also want a redundant server just in case this primary one crashes for whatever reason. I don't want my website to crash, so I want to rent for an extra $2 or $5 or whatever it is. I want to rent a redundant server just in case something happens and I want my service to go to that backup server. DNS poisoning is another concept, another big problem, and this has everything to do with malicious actors that are trying to attack your company. So if you are big enough, then you will have people trying to attack you. And this is unavoidable, unfortunately, because if you are big enough for a variety of different reasons, because either they want money from you or because they have some kind of a vendetta against you or because somebody hired them to do it, your competition wants to take you out, whatever, like just for a variety of different reasons, if you are big enough, if you are notable, if you have enough notoriety, then you are going to get attacked. Now, the issue with DNS poisoning is that it happens on the DNS server level. So if the DNS server has a vulnerability in it, that will leave it open to an injection attack, right? So if somebody poisons your DNS server and then they inject false information into your DNS cache, that means that they can now redirect your users. they can send them to their own website, right? So they have a domain name that looks very, very similar to your domain name. They purchased it to try to impersonate your domain. And now they're going to redirect all of your legitimate users to that domain because they want to capture their payment information, right? So you have, let's say Microsoft is the example here. Microsoft sells a bunch of services. You can buy computers, you can buy software, you can buy so many things from Microsoft. You can buy applications through their Microsoft application store. So there are so many different things that Microsoft actually charges money for. So if we are able to in some way poison their servers, then we can redirect their users, the millions of freaking users, probably billions really. We can redirect all of those users to go to our website and give us their sensitive data, their payment information. And then they think they're buying from us, and then they authorize the payment, and we're getting the money, but they're not getting anything in return. And then how many of those people are going to immediately report some kind of an issue, or how long will it take for them to even notice, right? So it will take some time. And during those 25 minutes, during those few hours that it will take for people to report the problem to Microsoft and for Microsoft to resolve the problem, during those few hours, whoever the attacker is can stand to make millions of dollars because Microsoft is a massive company. So if you can actually poison their DNS cache, you are going to make a lot of money. That's basically what it is. And again, this is just something that it's just unavoidable. When you're a big enough company, people are going to try to attack you, and they're going to try find as many different attack vectors to attack you, and this just happens to be one of them, which is DNS poisoning. The first step for troubleshooting DNS issues is to verify your DNS records. So use something like NSLookup or Dig or some kind of an online NSLookup. So nslookup.io is an online version. NSLookup by itself is a command line tool that you can use. But these are basically tools that verify the accuracy of your DNS records, right? So you do nslookup google.com, and then it'll say, yeah, google.com is pointing to this specific IP address. And then you can say nslookup and then give it the IP address and see if it points to google.com. So you can actually do both directions to try to see that all of the records are actually good. Dig is the same thing. You do dig and then you give google.com, and it'll give you the information about their DNS records. And then again, of course, you can just use an online DNS lookup. Check for typos, check for incorrect IP addresses, check for any other kind of error to see if this is actually an issue, right? And then a lot of there was this recent room that I did on TryHackMe where the DNS record was not resolving to the IP address of the target machine that I was supposed to be hacking. And as I was going through that, I looked at the configuration files that I was supposed to modify, and I looked at so many different things, and I modified everything that I needed to. And every time that I would run NSLookup, it still would not resolve to the IP address, and it ended up being a really big configuration issue from the end of from TryHackMe themselves. And then I emailed their support team, and then they fixed it, and then I was able to do the DNS configurations and the resolutions of the IP address to the domain name. So those things, sometimes when you actually go through this and you see that it's not working, you have to kind of reverse engineer and go to configuration files and look at your Etsy host file and look at your systemd resolve file, whatever. Like you start looking at configuration files to see if there's a typo in the domain name that's supposed to point to that IP address, or if there's a typo in the IP address, or whatever the other error is that you are having that it won't allow you to connect to that domain name. And then you want to test the DNS server's connectivity. So number one, you verify your records, right? You verify if the DNS configuration is all good, or if they're at the very least, if they're pointing to where they're supposed to be pointing to, and then you check for typos or incorrect addresses, so on and so forth. And then you have the DNS server connectivity, which you ping the IP address, right, to see if it actually is up. If you ping and then you give it the IP address, or if you ping and you give it the domain name, you will get a response. And the response is going to be one of two things. You know, it took a certain amount of milliseconds for the actual server to respond, and it'll keep responding, or it's going to say the server is not responding. That's it. That's basically the response that you will get. Some kind of a response. It's either going to be, okay, the server is responding, it's up, or the server is not responding. And you can ping the primary IP addresses. You can ping the secondary IP addresses of these servers to see if they're reachable or not. And then you would use a tool like Dig to check for the DNS server responses and troubleshoot any connection issues if there are any. Next, you want to monitor the propagation. So you can use an online tool. You can use DNS monitoring services to track the propagation of your changes across the internet. So basically, how long does it take for a change that we make to be globally accessible and available, right? So how long is our propagation process, and what can we do to improve that speed? Should we switch to a different hosting provider, or what do we need to do, right? So you can monitor how long it takes for changes to be implemented globally. The next one would be to implement DNS caching or caching. I think it's caching. I think that's how you pronounce that. I always say caching anyways. But so essentially, when you use a caching DNS server within your network, it improves performance and reduces the impact of propagation delays, which basically means that there is now going to be a cache of the DNS records on your computer or on your server, that instead of, if you can recall to what we were looking at with the various levels of domain names, and then you have my mind just drew a blank. You have your root server, and then you have your top level servers, and you have your authoritative servers. When you're looking at these levels of servers, all of those things could actually be inside of your cache, so that every single time you try to access a domain name, it doesn't have to go through that process every single time. When you implement the caching, it stores that data so that the next time that you want to access that given website, it just automatically says, oh, I know exactly what IP address belongs to Google, so let's just go to that. I don't need to go through the root and then the top level and then the authoritative servers to actually be able to find the IP address for this. I know exactly what the IP address is. Let's just go there. So that's what caching does. It's essentially like a database of all of the domain names and the IP addresses that are assigned to them, and then it just quickly goes to that IP address immediately. So caching servers store the frequently accessed DNS records locally, and it reduces the need to query the upstream servers repeatedly. So it increases speed drastically. Now, whether or not this would actually help your DNS configuration issue is a different element. This is mostly for just increasing speed for being able to access a website. And that's also the reason why it's number 4. Like, it's, if you have a configuration issue and you can't access the website, it has nothing to do with your DNS cache. It's more likely something else that is happening, and you need to go address all of that stuff. And then if you wanted to just load faster, then you can implement DNS caching. And of course, as an extra layer of measure, as a really good best practice, kind of a good habit to have in place, would be to implement DNS security measures. So the DNS security extensions, which is DNSSEC right here. If you implement this, it enhances the security and integrity of your DNS data. If you utilize DNS firewalls to filter DNS traffic and block malicious queries, you could do that. And pretty much with every firewall, my default rule is deny everything, and then explicitly allow these ranges of IP addresses or devices to be able to access me, right? Deny every port that's trying to access this IP address, only allow port 443 because I know that it's an encrypted HTTPS. You know what I'm saying? So it's like there are different ways that you can set up your firewall configurations. My approach is deny everything and then explicitly allow the sources or the people that you think should be able to access your servers. And this could be for the DNS server. It could be for a given machine in your network. Doesn't really matter. That's just kind of my approach to this thing. Regularly review and update the DNS server software and configurations to address known vulnerabilities. And this has to do with patching, and it has to do with updating. And this is another one of those good practices that you should not wait for a vulnerability to be known. You should not wait for an attack to happen against your servers or against your infrastructure. You should be doing this regularly. It should be a scheduled review and update of the server software and the configurations to make sure that you stay ahead of whatever the vulnerabilities are that would come out. Now, mitigating DNS misconfigurations, I mean, you've pretty much heard this throughout this entire training series, and we literally just went through a very similar list for the DHCP misconfigurations, you want to do thorough testing, you want to do regular monitoring, you want to properly document everything, and you want to do regular maintenance, right? Conduct a thorough testing of your DNS changes before implementing them in a production environment. Do it in a controlled environment, in an isolated machine, in a sandbox environment before you implement it through the rest of your company. Monitor everything regularly, right? Monitor the DNS server performance, look for signs of misconfigurations or security breaches inside of your logs. If you're implementing something like a SIM, then your DNS logs will be something that will be ingested by the SIM, and then the SIM will point out anything to you that would be of note. Maintain accurate, up-to-date documentation. Have a good playbook, right? Like have good documents, have good notes. And then a regular maintenance task like software updates, security audit, all of these things, very, very basic concepts. These are common sense, and you should be doing them for everything that we're talking about, not just DNS or DHCP or just service. You should be doing this regularly. This is a part of your job as somebody who is in IT. So by carefully assessing or addressing these issues and implementing appropriate mitigation strategies, organizations can ensure the reliability and security of their DNS infrastructure and minimize the impact of misconfigurations on their operations. Our next issue is the misconfigured routing table. And so routing tables are data structures within the network devices, so the router, the switch. And these tables store information about how to forward network traffic to the various destinations. And each entry in a routing table typically includes these three things: the destination network, so the network address or the range of addresses; the next hop location, so the address of the next device, which is the router that should receive the traffic; and then a metric, right? So the value that's used to determine the best path to that destination. For example, the count of the hops, the number of hops that it would take, the amount of bandwidth that would be associated with it, or it took, the amount of time that it took for it to get to that next hop, right? So these are the metrics that would be a part of the routing tables. So you have the destination network, the network address or range of the addresses that it would be trying to visit. You have the next hop, which is the very next device, the very next router. So when you look at the trace route command, for example, it basically just gives you the address of the routers that packet hopped across to be able to get to its destination. And one of those routers will be the router of your internet service provider, right? So it'll leave your network and it'll take however many hops it needs to get to your internet service provider router. And then from there, it'll take however hops it needs to be able to get to your destination address, wherever it's supposed to be ending up. The misconfigurations for this would be errors in these tables that can disrupt the normal flow of network traffic, and they lead to connectivity issues, performance degradation, and even network outages, right? So a misconfiguration for your routing table can actually be kind of detrimental. Like it can actually mess with your network performance, as like it can halt network performance basically. The first common problem for this would be that there's an incorrect route, right? So the next hop is incorrect. The traffic can be directed to the wrong router or interface, and then that leads to a dead end or a black hole where the packets are dropped, right? So if the next hop is wrong, then it's literally just going to stop in its tracks. It won't be able to move on. The incorrect destination, so routes may be incorrectly defined for specific networks or subnetworks that actually causes traffic misdirection. So the destination address is it could be wrong, right? This is all part of the actual route that something is taking. And then there's the routing loop, which is the circular path. I mean, it's a loop, right? So it's a circular path where packets endlessly traverse the same set of routers, and then they never reach the destination because they're literally in just in a loop. So this can severely impact network performance and even cause network instability, obviously, because all of the packets are just basically going in a loop, ending up at the place that they started from, going in a loop again and going in a loop again. They're not doing anything. And then if it happens to every freaking packet that's trying to leave your network, then your network just crashes. It's and it takes up bandwidth, right? Because it keeps trying to resend the packet over and over and over again, because it thinks that, oh, okay, this came back, maybe there was some kind of a temporary issue, so it just keeps retrying to send that packet out. Now, if this is happening with millions of packets, because you have hundreds, if not thousands, of computers that are trying to interact with the internet, then you're going to have a really big problem in your network. It's going to take up all of the bandwidth of your network, and ultimately the network itself is going to crash, and then now you got to go try to figure out what the hell just happened. The next problem would be the default route is missing, and the default route is a special route that specifies the next hop for traffic that is going to any network that's not explicitly defined in your routing table. So let's say you have a list of networks in your routing table that the next route or the next hop is already predetermined, right? So the packets that are leaving your network, they know that if the routing, the network that they're trying to reach is inside of your routing table, they know where to go. Now, if the network that they're trying to reach is not inside of your routing table, then there needs to be at least a default location that packet knows, okay, so if it's not in this routing table, then I know at least my next hop is to go to whatever this default route is. So if you don't have that, then the device can't forward traffic to an external network like the internet, and then it leads to complete loss of external connectivity. So it's like you need to have some kind of a default route for everything that is not explicitly defined in your routing table. Now, the static versus dynamic route conflicts is another one. So a static route is manually configured routes that override dynamically learned routes. Dynamic routes are learned automatically by routing protocols like RIP or the open shortest path first or the border gateway protocol, etc. And then the conflicts are when the static routes are incorrectly configured or have higher distances, administrative distances, which is a lower priority, than dynamically learned routes. They can interfere with normal traffic flow and cause routing issues. So I'll read that one more time. When a static route is incorrectly configured or it has a lower priority than a dynamic route, then they can interfere with normal traffic, because manual configured routes, these static routes, actually have higher priority because they override the dynamically learned routes because somebody manually configured them. So obviously they override the dynamic routes. Now, if that static route, okay, that is supposed to override, it's supposed to have a higher priority. If that static route has a lower priority, then there's going to be an issue, right? There's going to be interference with normal traffic, and then it's going to cause routing issues. This one's kind of fun to talk about just because I like the word flapping. So if we have routing table flapping as one of our problems, this means that there's rapid and frequent changes to the routing table entries, and the causes of this would be oscillating link conditions. So the link conditions oscillate, right? They're moving quickly, which means that there's intermittent connectivity. That's an example of this, right? The configuration errors in routing protocols or routing loops are all causes of this flapping concept. So the rapid and frequent changes to the routing table entries. The consequences of flapping is that the network instability, performance degradation, and increased CPU utilization on your routers is going to be a consequence. It's actually going to happen. So the network will not be stable, performance will degrade, so performance will deteriorate, essentially it'll slow down. And then of course there's going to be increased CPU usage on your routers. Your routers are going to be overloaded because there is constant changes that's happening to your routing table entries, and they are rapid, meaning they're fast, and they're frequent. So it's just going to take up the CPU, the processing power of your router. All right, so to troubleshoot our routing issues and the routing table issues, the first thing would be to actually inspect the routing table. So using a command like route or netstat or IP route, depending on your operating system, to actually examine the routing table on your router or other network devices. So the routing table, and I should have probably said this earlier, the routing table is essentially the list of destinations within your own network that your devices know that they can go to, and then the default route of the routing table is the destination that they would go to leave your network and to actually go to the external network, which is the internet, right? So if there are any incorrect or unexpected entries in your routing table, that means that there is some kind of an issue that you need to look at. So you would need to first find what your actual routing table for your network looks like. If there's an issue with your machines or with your devices trying to connect to each other within your routing table destinations, that means there's something. So first you would look at just the routing table itself just to see what it actually looks like and what the entries look like and what the default route looks like and all of that. And then you can see what the next step would be that you would have to take. And the inspection of your routing table could be, if the devices can actually connect to other devices, if they can communicate to other devices inside of our local area network, but they can't connect to the internet, then there's something wrong with default route. But if they can connect to the internet, but they can't connect to the other devices inside of our local area network, inside of our local network, then the default route seems to be fine, but there's something wrong with the addresses that are listed in our routing table, okay? Verifying the network topology. So compare the routing table entries with your actual network, the physical network topology, and ensure that all the routes are correctly configured and reflect the desired network design. So this is another element. Again, if you're looking at your network topology, that means you're looking at your local network and the way that your local network is set up. And then based on that, you would say, okay, well, either this looks good, or if it doesn't look good, etc. So you can be able to narrow down what the problem is. Then you want to check for overlapping routes. So identify and resolve any overlapping or conflicting route entries that may be causing traffic misdirection or looping potentially. Then you want to analyze the routing protocol logs. So look at the logs of routing protocols. So for example, the RIP or open shortest path first for any error messages or warnings. And again, logs are just a really good source of information to try to narrow down what's going on. And identify and troubleshoot any routing protocol issues that may be contributing to the misconfigurations. Then you want to implement routing filtering or implement route filtering, which is the configuration of your filters, of the route filters, to prevent the propagation of incorrect or unwanted routes within your network. So filter the routes that some packets can take or they should not take. Basically, that's what that means. And this is very similar to, well, I don't want to say very similar, but it's kind of similar to the concept of what a firewall does, because the firewall filters traffic essentially. So you can also design your network routing table to actually filter the routes that packets can take to prevent propagation or unwanted routes within that network. And then you can use network monitoring tools, right? So monitor the network. So use network tools, monitoring tools to identify and troubleshoot routing issues proactively, and monitor your network traffic patterns, identify anomalies, pinpoint the root cause of connectivity problems. And all of that can be done by a monitoring tool, and then just staying ahead of whatever the problem is. You don't have to wait for there to be an issue to be able to solve the problem, right? So this is one of those things that can be done if you're actively, proactively monitoring your network by just using a monitoring tool. Think about it. How crazy is that, right? It's like, it's such a what is it? A novel concept, right? It's like amazing. How's that? All right. The routing table misconfigurations or routing misconfigurations also have a very similar list of mitigations. So thorough planning and documentation, plan and document network topology and routing configurations before implementing. Change management procedures, so implement strict change management procedures to minimize the risk of introducing errors during network changes. And then of course, conduct regular audits of routing tables to identify any and correct anything before a big problem arises. Test all the network changes thoroughly in a controlled environment before implementing them in production. Implement redundant routing paths. This is actually a new mitigation specifically in the list that we've talked about so far anyways. So you want to implement redundant routing paths and failover mechanisms to ensure network resilience in case of routing failures, right? So have backup routers just in case, and have them be connected and available at the drop of a hat, right? In case something happens with one of your routers or with something that's going on with your physical infrastructure. So you have redundant routing paths, right? A route or a packet that leaves your network to try to connect to another router inside of your network or outside of your network, it should have multiple paths that it can take and then using something like the open shortest path first, the OSPF protocol, it can say, okay, well, this is my shortest path that I'm going to take. But if this path is not available for whatever reason, at least I have a secondary path that I can take. And that could be based on the network topology. It could be based on a variety of different reasons. But the topology itself, if you think back about the mesh topology that we talked about, there are so many connections inside the mesh topology, which provides for a massive redundancy, that in case one of those routes fails, in case one of those wires or one of those things doesn't work, that packet has another 5 different ways or another 10 different ways that it can leave that network and still be able to get to its destination. So that's where redundancy comes in. That's where having a fail-safe or a failover plan comes in. So by carefully planning, implementing, and monitoring routing configurations, network admins like you can minimize the impact of misconfigured routing tables and ensure reliable and efficient network operation. All right, these next few sections, we're going to kind of breeze through these because these are a little bit easier to understand. So a performance bottleneck, which is also known as a bandwidth constraint. And bandwidth is the maximum amount of data that can be transmitted over a network connection in a given time. So insufficient bandwidth leads to congestion and slow performance. And the cause of this could be the oversubscription of links or overuse of links. It could be a high volume of streaming or backup or file transfers that are happening all at the same time. And the mitigation would be to implement quality of service policies, to prioritize critical traffic, to just make sure that the stuff that should be getting across the network or outside of the network can do that before, you know, some kind of streaming or whatever, like some BS thing that people are trying to do. So the quality of service policy prioritizes the important traffic. And then you upgrade your network link to higher speed connections, which is a really good idea. Use better cables, use better routers, use a better internet service provider, right? There's different ways that you can make sure that your bandwidth is stronger. And then monitor the usage of the bandwidth like NetFlow or Wireshark, just to make sure that there's not an overwhelm of the demand, the resources that are available for that network, and those resources aren't being demanded by not critical services or devices. So you just want to monitor, right? Monitoring, again, is another one of these key concepts here. Another performance bottleneck would be the concept of latency. So this is the delay between a data package transmission and receipt, measured in milliseconds. So this is the speed that data travels, essentially. The causes of this could be geographical distance between endpoints, high router or switch processing times, congestion at intermediate hops. So if you have slow latency or low latency, meaning that it's taking too many milliseconds for this packet to travel, this is an issue, right? So the impact of this could be real-time applications like voice over IP, which is your phone that's connected to the internet, and online gaming experiences, which is not as big of a deal, I guess, unless you're talking to the gamer who's getting shot or, you know, losing the game. Unless that is the issue, it's most likely like, okay, well, we have a problem with our connection and our customers that they're trying to access their accounts, or we're trying to access accounts to make some kind of a change to the customer's account, but I can't because the internet is slow, right? That could be an issue. The mitigation technique could be to reduce the number of network hops by optimizing routing, if you can, to use content delivery networks like CDNs to localize your content, or to upgrade your hardware to lower processing delays, right? If you can update your hardware, that's probably a really good idea. If you can use really strong routers or good cables, all of these things are really good. To go from a copper wire, which is kind of like the oldest type of wire in internet communications, to fiber wire, that's an upgrade in your cabling, and it's going to significantly improve your internet speed. And the next bottleneck is our jitter. And this is the variation in the packet delay across the network. So jitter, think about jitter as a variation in the latency, right? So this is the variation in the speed of the speed of your network and how quickly things can go in and out, and the variation in that speed. So there's congestion causing inconsistent packet delivery times. There's queuing and buffering delays on intermediate devices, and this can cause VoIP calls or video conferencing to suffer from choppy audio and video, and it can cause what you're expecting a transaction to take a certain amount of time, but then now there's jitter, and the transaction is taking longer than usual, and you estimated that you would be at a certain task for a certain amount of time, but now it's taking longer because there's jitter inside of your network, and then you promised your manager that you would end up doing something in a certain given time, and now you can't. So you have to tell your manager, hey, there's speed that's going on, and I can't deliver on time because the upload is taking longer than I thought, right? Something like that. Mitigation techniques would be to implement quality of service to prioritize real-time traffic, to use jitter buffers in VoIP systems, and of course monitor your network, right? It's not on here, but that's always one of those things, like monitor the network, stay ahead of this, and try to see if you can catch it before it actually causes big problems. So to kind of summarize everything that we've talked about, if you want to diagnose and mitigate network performance issues, there are some key tools and techniques. So you can use ping and traceroute, which are command line tools, and you can use those to test the connectivity and identify any kind of latency or routing issues for packets that are leaving your network. Another one would be to monitor the bandwidth using the SolarWinds, monitoring NetFlow, Wireshark, to actually detect congestion and usage patterns inside of your network or for traffic that's leaving your network. Applications performance monitors, APMs, analyze the impact of network performance on applications specifically. And then the load balancer that distributes traffic evenly across multiple servers to prevent overload. In case you're housing your servers, you have on-site servers, or if you want to rent a server from Google Cloud or AWS or whatever it is, you should rent multiple servers and then use a load balancer to distribute the traffic evenly so that not one server is getting overloaded. And then in case anything does happen, you have backup servers for redundancy, etc. And now we can look at some scenarios here. So resolving a DHCP scope issue, the problem is that users can't obtain IP addresses. They can't get IP addresses. So you would increase the IP address pool, meaning the scope, right, the range of the IP addresses, and then reduce the lease time to free up unused addresses. Scenario 2 would be addressing the DNS resolution failure. The problem is that employees report that websites aren't loading. So you would correct the A records for IPv4 and quad A records for IPv6 and ensure that the DNS server is actually reachable. Scenario 3 would be mitigating routing table errors. The problem is that traffic is being routed incorrectly between the subnets inside of your network, because remember, the routing table has to do with the locations of your internal network, and then the default route would be when it's trying to leave your network and go to the internet. So the solution is to add missing routes and correct default gateway configurations. So just make sure that you actually have configured any missing route that the traffic is trying to take. And you would also be able to find this by looking at where the packets are trying to go, where that data is trying to go as it's leaving your network. And you would notice, oh, okay, this is actually a missing route. It's not on our routing table. And then correct the default gateway to make sure that they can actually leave using the proper router, and then they actually have a path to follow when they do leave. Scenario 4 is reducing the bandwidth bottleneck, and the problem is that the video conferencing quality degrades during peak hours because a lot of people are trying to do video conferencing. So we implement the quality of service to prioritize VoIP and video traffic over non-critical services because the video conferencing is important, right? People need to finish their meetings. And then there are certain parts of the day where meetings are really, really high and people just need to be able to get those things done and accomplish the task. So you can do quality of service implementation to prioritize the VoIP and video traffic according to either the ports that they use or the applications that they use or the protocols that they use, and you prioritize them over the non-critical stuff. Scenario 5 is managing latency in a remote office. So latency again is speed, right? So the problem is that file transfers between remote offices are slow. So we want to deploy a content delivery network. I believe that's what it was. Deploy a content delivery network and optimize routing to minimize latency. Okay. Which brings us to our practice questions. So here we go. What is a common cause of IP address conflicts in a network? Overlapping DHCP scopes, yes, that could be true. High latency on the network. High latency is fast speed. Or actually high latency would be high milliseconds. So it could technically be slow speed. Misconfigured routing tables, DNS propagation delays. So IP address conflicts in a network has to do with DHCP scopes. So overlapping DHCP scopes, yes. Which tool is commonly used to verify DNS resolution issues? So NS lookup has to do with DNS resolution. Traceroute is for routing. Netstat is also for trying to find the routes or the routing. Ping is to try to see if a server is up and if it's going to respond. So DNS resolution is commonly for NS lookup. What is the primary role of a default gateway in a routing table? To resolve domain names? No. To provide a backup link for redundant routing? No. To route traffic destined for external networks, to assign IP addresses dynamically. So this is DHCP. Backup link is redundant routing. So this is not a primary role of the default gateway. The default gateway is the first location. So we're not talking about a backup link here. Domain name to IP addresses, that's DNS. So traffic destined for external networks is the part of the default gateway. Which network performance issue is caused by insufficient bandwidth? So jitter is the variation in speed. Latency is the speed. Packet loss due to congestion could be insufficient bandwidth. High CPU usage on devices, not really. I don't think this even has anything to do with it. So it would be packet loss. Great. What is the purpose of quality of service in a network? So this is us trying to prioritize the criticality of the services that are trying to access resources, right? We're trying to prioritize which service can get access first. So to enforce stricter security policies, prioritize, there we go. So prioritize critical traffic and reduce congestion. That would be the answer. Monitor network usage in real time, eliminate the need for dynamic address. Prioritize, literally the key word here is prioritize. That is the one. What does jitter refer to in a network? It's the variation of packet delivery. I mean, that's the answer. So total delay, no. Maximum bandwidth available, no. Amount of data lost, no. So it's the variation in delivery times. Which of the following can cause a DNS resolution failure? Incorrect or missing DNS records? Yes. Low bandwidth? No. High latency? No. Misconfigured default gateway? No. So it's incorrect or missing DNS records. What is the recommended maximum length for Ethernet cables to avoid attenuation issues? Oh, this is interesting. I copied this from the last one. This doesn't even belong to our segment here. I mean, it's 100 meters, but it doesn't even belong to this segment. Which tool is best suited for identifying bottlenecks caused by routing table errors? So bottlenecks for routing tables, it could be Traceroute, it could be Wireshark. Ping is just to see if things are up. SNMP, I feel like this is also a duplicate. Let me see. Did I get these things right? I feel like I duplicated too many things. So Traceroute is identifying bottlenecks caused by routing tables. Okay, so all right. So what is a likely solution for reducing latency in a geographically dispersed network? Okay, this actually, all right, this belongs to us, to this section. Likely solution for reducing latency in a geographically dispersed network. Enable ARP inspection using content delivery networks, increasing DHCP list time, disabling quality of service. So quality of service, no. You want to enable that, so that's not the answer. Increasing DHCP lease times is also no. That has to do with IP addresses. ARP inspection has to do with whether or not MAC addresses are resolving to the correct IP addresses, and if we're getting poisoned or anything like that in our MAC address, frames and the packets and things like that. So content delivery networks, the CDN is the answer. And that's it. So with the exception of that one question, the one question about the length of the wires, that was pretty much it. So now we can actually go into tools and techniques, which are really cool because we're going to be talking about more physical tools that we would end up using, as well as, of course, the logical tools and the command line tools. And then this is going to be the last section for the lecture. And then after this, we're going to dive into the practical exercises to try to get everything that we need for you to know what you're doing, the actual experience that you need to become a really solid network admin. So let's go into tools and techniques. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. This is where all of the stuff that we've talked about will end up meeting the road, where the rubber meets the road, so to speak. Everything that we've talked about so far has been mostly conceptual and theories and philosophies around networking and the various ideas inside of networking. But then there are the parts where you just have to know how to implement these things. So how do you actually check to see the connectivity inside of your network or with a domain name? How do you check to see what the IP address of the individual machine is? How do you capture the packets that are going in and out of your network or in and out from a specific interface? And then how do you analyze those packets to actually see what type of data is being transferred back and forth from those various packets and from the interfaces that are being measured? So there's a lot of different tools that are available, and most of them are free. Most of them are open source that we're going to be talking about. The physical tools themselves are not free unless you're working for a company that provides them to you. And obviously, I'm going to be showing you a lot of physical tools as well and showing you what the purposes of those tools are. But the software tools, the command line tools, and a lot of those things are open source, and you can actually access them for free by simply just going to their website and downloading it directly from their website. Don't download it from some kind of a pirate website. Only download them directly from the actual source to guarantee that you're getting the proper software and it hasn't been modified and there's no bad injections that have been done into it, and they're not infected, therefore they don't infect your actual computer. So we're going to be using Wireshark, which is a really powerful tool. We're going to be using the Cisco Packet Tracer. We're going to go through the various command line tools that are available. So there are a lot of really, really great stuff. First, in this particular section, this is our very last section of the lecture, where before we actually start going into the practical portion of this training series, we're going to just overview what these tools are, what they do. I'm going to give you some sample either screenshots or commands or something like that. And then, of course, for the physical tools, you'll actually get to see the hardware tools and everything that goes along with those guys. And then from there, we'll go ahead and do the practical portion of this series, where you actually get to see how these tools are used. So let us jump into it. All right, our first category is going to be the command line tools, our software-based tools. And the first tool in this category is the ping tool. Now, ping tests the reachability of a device, basically tests whether or not it's up and running or it's down, or maybe it's blocking the ping requests that we would send to it. For the most part, if it's not responding, it's either because the service is down, the actual device itself is down, or they're blocking ping requests, which is also part of a security thing that is done to prevent denial of service attacks from taking place. A ping request is an ICMP echo request that gets sent out. Now, when there's a denial of service attack that happens, they get flooded with ICMP packets, right? So they get millions and millions of packets that essentially either slows down their service or just makes their service completely crash. But in a normal environment, if we're not worried about that kind of situation and we just want to see if something is up, we would send out the ICMP request, the ping request, and it would send out an echo request, and the system would send out an echo reply if it's up. Usually, if it's not up, it says, not reachable or response not available. I forget what the actual term is, but either you will get responses, you'll actually get echo replies from the system, and they come every fraction of a second. So they'll come back, every 65 milliseconds or something along those lines. Or if they're slow for whatever reason, maybe they'll come every few seconds, but at the very least, you'll get some kind of a response. And then if the system is not responsive, you will not get any kind of a response. It'll typically say not responding, or system is down, service is down, something like that. So the first portion of it would be to actually check to see if you can connect to the device, if the device is up. The second reason for it would be that we just want to see how quickly the host that we're trying to connect to will actually respond to us. And if there are any packet losses. So usually if you just do the ping by itself and then give it the host name or the IP address, it'll just keep running until you stop it from running. So it'll literally run indefinitely unless you actually do Control-C and you stop it from running. So what you can do is you can actually do ping, and then you can use the -C flag for count, and then give it the count of requests that you wanted to send out. So you can say -C and then do the number 10, and it'll send out 10 echo requests. And then if you get 10 echo replies, that means there was no packet loss. But if you get, 8 echo replies, that means you lost 2 packets, either by sending out the request or from the reply. In one of those situations, the packets were lost. So you can say that the reliability of this connection isn't that great, right? So, but you will also get a response as far as the speed of those replies are concerned. And based on that, you can determine how strong your connection is, and if you need to work on something to troubleshoot your connection. On Windows, it would be ping and then hostname IP. On Linux, it would be ping as well as hostname IP, and then you can just include something like the -C. I believe you can also include the -C on Windows as well. It should not be subject to the changes in the operating systems. It should be pretty consistent across all of the operating systems. And that's basically it. So for example, you do ping google.com, and then you see if you can actually connect to Google servers and if there are actually responses that you would get from Google servers. And usually it'll give you, for the most part, as long as it's up, it'll actually give you a response. And of course, we're going to run this when we go to the practical section. I just wanted you to be aware of it because we've already mentioned it multiple times throughout this series. This is an official declaration that there is a tool called ping, and we use it to check connectivity and measure packet loss as well as the speed of the response. Traceroute is another tool that we use to check connectivity, mostly to check to see the route that a packet takes to reach its destination. And typically the maximum hops would be 30. So if it goes from one router, so your router, right? If it leaves your router and it goes to the next router, that's one hop, and it'll go to another one, and it'll go to another one. And somewhere along that path, it will go to the router of your internet service provider. And then from there, it'll take a few more hops, and then it'll reach its destination. And it maps that route. So it'll map basically how many hops it took to reach its destination. You want the least number of hops because it'll be faster if that happens. You can also measure where the packet was lost or where the signal itself was dropped based on the router that it tries to connect to, and then it's not able to reach the next router because it keeps getting dropped at this one particular router. That could be one of those reasons why you would lose the connection, or the hop would be dropped, or the packet would be dropped. So the use cases for traceroute is to identify bottlenecks in network paths, meaning congestion, right? There's a lot of traffic going to a specific router, and then it's slowing the progress of those packets along the remainder of its route before it can actually reach its destination. So you actually want to see each hop along the path as well as the delay in that, and that's where the bottlenecks itself can actually come in. And then, of course, diagnosing latency, which has, again, to do with the speed of the delivery of these packets, which then also connects to the delay. So this helps you map the route that it actually takes, including the router that your internet service provider is providing. And then from there, you can figure out if there are bottlenecks, if there's any packet loss, if there are any latency or speed issues. And the syntax is actually different based on the operating system. So if it's a Windows operating system, it's traceRT, and then you give it the hostname or the IP address. And if it's a Linux operating system, you give it traceroute, and then you give it the hostname IP address. And traceroute also applies to Unix, essentially being Mac OS operating systems as well. So if it's Unix or Linux, it'll be traceroute. If it's Windows, it'll be traceRT. And then this is an example, right? Trace RT. So this is assuming that we're using a Windows machine. And then we're doing google.com to trace the path that the packets will take to actually get to Google's servers. Next, we have NSLOOKUP and dig. And so for the most part, they do the same thing where they actually get you the DNS records or the DNS connection of a specific domain name. So for example, if I do NSLOOKUP example.com, it'll give me the IP address for example.com. And that's basically it. That's what NSLOOKUP will give us. And there's actually a website called nslookup.io in case you don't want to use your own IP address to search for the DNS resolution or the DNS records of a specific domain name. And then you can also do NSLOOKUP and then give it the IP address, and it'll tell you if it's connecting to a given domain name. So when you do the domain name, it'll give you the IP address. When you do the IP address, it'll give you a domain name. And now what happens with dig, so this is the domain information groper, and groper just sounds so bad, but dig provides advanced DNS records. So the same thing that you would get with NSLOOKUP, but it also gives you the detailed output. For example, who registered, who is the registrar. If their records are not private, it'll give you the contact information and the address and the phone number of the person who owns the domain. And there's a lot of records that actually comes from running dig. And so we can do example dig example.com. That could be our syntax example for this, and it will just give us DNS records. So if you're trying to see if your specific domain name will actually connect to an IP address, or if the IP address for your domain name has actually been resolved, if it is getting resolved, you can just run NSLOOKUP. And I've used NSLOOKUP a lot of times when I'm testing a lab environment, because there are certain tools like, for example, GoBuster. When you use GoBuster, it's a pen testing enumeration tool. When you use GoBuster and you want to use it in its DNS mode, you need to run it with a domain name. You can't run it with an IP address. And in order for that to happen, the IP address has to resolve to the domain name and vice versa. Otherwise, GoBuster won't run. And for that, you can either modify the configuration file for systemd resolve configuration, or you can modify your etc host file. There's a variety of different things that you can do as far as configurations are concerned to make sure that the IP address is resolving to the domain name and vice versa. But essentially, the goal here is to diagnose DNS resolution problems, right? Verify DNS records and test DNS server responses. That's essentially what we're doing with both of these tools. They're designed to get you DNS records, verify the resolution of the DNS to the IP address, and vice versa, and help you diagnose if there are any DNS resolution problems. Then we have ipconfig and ifconfig, and ipconfig is the Windows version of this, ifconfig is the Linux version of this. And then there's the more recent version, which is IP by itself. You just do IP and then you can do -a, and then it'll give you essentially the same response that ipconfig or ifconfig would. It's just a little bit more recent. So depending on the distribution or the version of the operating system that you're running, it may be that tool. But for the most part, on my MacBook, it runs ifconfig, so that actually works. IP is not installed on my MacBook. The ifconfig command was the one that came pre-installed on my MacBook. And so you can do ifconfig just by itself, and it'll give you a pretty long output of all of your interfaces and the IP addresses that are connected to your interface, as well as the IPv4, IPv6, the subnet, and everything else that belongs to it. And then you can do ifconfig and then give it the actual interface name, and it'll give you all of the details for that specific interface. And an ipconfig/all, very similar to what ifconfig just by itself does as well. But it's the Windows version of it. So it will display the network configuration like the actual IP address of your machine, the subnet mask that you belong to, the default gateway that you connect to, and the same thing works for ifconfig as well. And for the most part, you can get the IPv4 and IPv6 addresses. For Windows, I believe you actually have to use the /all to be able to get all of that stuff, because by default, if you just do ipconfig, it'll just give you the IPv4 addresses for your interfaces. But if you do ipconfig/all, it should give you all of the details, including the subnet and everything else. And an ifconfig, in this particular case, if you just do ifconfig by itself, it'll give you all of that data for all of your interfaces, or you could do ifconfig and give it a specific interface, and it'll give you the details for that. So we would use this to check IP address and network settings for our devices. We would use it to verify connectivity and troubleshooting interface issues for all of our interfaces, and that's essentially it. Next, we have NetStat, and NetStat displays active network connections, listening ports, and protocol statistics. So active network connections fall under the established category. So when you see something that has a status of established, that means that's an active connection that's going on. And then you can look for listening ports, you can look for protocol statistics, and we use this to identify the open ports and associated processes to those ports. So we want to see what's connected to the list of open ports that we got, what kind of process or service is actually running on that port. And then we also want to monitor active connections for any unusual activity that may be going on. And these are your established connections. You want to check to see what is actually going on those ports. So for example, if somebody is using Metasploit to create a reverse shell to your ports or to your protocols, you can actually see that connection. And then if it doesn't make sense, if it's a fishy port number, or if it's something that is not normally in your list of connections, you can try to see what that actually is and what's going on with that. So these are the actual examples for this. So both of them actually go for NetStat. And then -A, this is a Windows version where we do -A and it displays all of the active connections. And then if we do -T by itself, it'll be TCP. If we do -U, it'll be UDP. And then when we do -L, it's listening. And then N, it does not resolve the domain name to the IP address. So it actually just gives you the IP address for this. So we would have TULN, which gives us all of the listening ports and the protocols that are associated with it. And when we say all listening ports, we're talking about all TCP and UDP ports. That's how we can look at it like this. So this is the Linux version of this. The NetStat version of it for Windows is also, I believe that again, once we kind of go through the testing stuff, we can actually just see if it is exactly the same filters. But for the most part, I believe that it is exactly the same filter. So you could technically run the same exact command on Windows as well, and it will give you all of the TCP, UDP listening ports, etc. So all of this information for these various tools, unless it's been specified, they've pretty much run the same exact way. So NetStat is used to display active network connections, the listening ports, protocol statistics, and we use it to identify ports and associated processes and monitor active connections for unusual activity. Our next tool category is the software tools, and the first one here is Nmap, is the network mapper. Now, Nmap actually has a graphical user interface as well as a command line version of this, and for the most part, I've only used the command line version. It's much faster, and I feel like the syntax is fairly simple to learn and understand. And it is a very powerful tool. It's one of these industry standard tools that are used for enumeration of a network, to actually discover the IP addresses on a network, to discover the operating systems, the versions of what is installed on these various IP addresses, as well as the open ports on those IP addresses. So you can actually get a list of all the IP addresses, get a list of all the open ports on those IP addresses, and what is installed or what is running on those open ports. And for everything that I've done for it has been under the guise of security, in the context of security. So I use it for mapping a network based on what we want to do for a penetration test. But it is a tool for network discovery, because you can literally enumerate all of the IP addresses inside of a subnet based on a very simple set of commands. So the key features are that we can scan networks to identify the host, the services, and open ports on it. We can also detect operating system and software versions. We can see what vulnerabilities are installed on any of those open ports, or not installed, I guess, what vulnerabilities exist on those open ports, because there is a a list of vulnerability scripts that is actually available with Nmap. You can just run some of its in pre-embedded scripts to try to discover vulnerabilities on any of the given ports and the various services or operating systems that are running on it. So it's a very, very, very powerful tool. We can use it to assess network security. We can use it to identify vulnerable systems, to map out the network, as the name implies, to actually see how many IP addresses are on any given network or a subnet. So again, very, very powerful tool, very useful. The basic scan is Nmap, and then you give it the target IP address, and it runs a TCP scan where it actually tries to make a full connection to the target IP address instead of doing just a SYN scan or something like that. So we did talk about this a little bit earlier. So the TCP scan is much louder when it comes down to an intrusion detection system. It definitely shows up because you're trying to do a full-on connection to a given IP address or a given port. There is a variety of different scans that we can run with Nmap, and we will definitely run them in the practical section, but there are some sneaky ways to actually run the Nmap tool so that you aren't as loud, so to speak, when it comes down to intrusion detection systems. You usually don't show up. So there are a lot of different ways that you can kind of bypass the intrusion detection by either kind of limiting the number of packets that you send out or the type of scan that you run. And so this would be our basic detection. You just run Nmap, and it'll just run for whatever the IP address is. It'll give you what the open ports are based on the responses, and then it'll say at least what protocol is running on those open ports. It's not going to give you versions or operating systems. If you want an OS detection, then you would do Nmap-O, and then you would give the IP address, and then it'll tell you what type of operating system is running on each one of those open ports. And then you can do, again, I'm kind of getting ahead of myself, but there's so many different flags, so many different options that you can run with Nmap to give you the software version, to give you what vulnerabilities exist, and to enumerate the map of the network to actually see how many different IP addresses are actually on a given network, and etc. So it's a very, very powerful tool. You can learn a lot from it. You can learn a lot about a given network from Nmap. So it's a very, very powerful tool. So yeah, that's it for Nmap. We are definitely going to use this one. It's a very, very important tool, and I am excited to share about it with you. There's a lot of videos already on this channel about Nmap as well. So if you are interested in doing some independent study and learning advanced Nmap strategies, I would highly recommend you check out those videos as well. Then we have our Wi-Fi analyzers. So these monitor and diagnose the wireless networks that are available in your network, which provide insights into the strength of the signal, if there is any interference with that signal, and which channel it's actually using, among other data as well. Some of the most popular tools here are the NetSpot Insider, so SSIDER Insider, and then of course Wireshark. And then we have the mobile apps as well, so which is the Wi-Fi analyzer for Android, and then we have Airport Utility for iOS. And again, these are just really useful, powerful tools. And then there's, of course, the penetration version of these Wi-Fi analyzers like AirCrack G. Very, very cool tool, very powerful tool. It is outside of the scope of Network Plus, but it is a very cool tool for pen testing Wi-Fis. And then we have the use cases here. So identifying interference and optimizing channel selection, and then troubleshooting weak signal areas, also known as the heat map. So this, for the most part, I don't know if, I know for a fact that Wireshark doesn't generate a heat map. But as we go to try to use these various tools here, we'll try to see if we can generate a heat map. If not, we will most likely talk about certain tools that actually do generate a heat map, meaning, the closer that you actually get to the Wi-Fi access point, the wireless access point, it'll be hotter, so to speak, because the connection will be stronger. And the further that you get away from that wireless access point, it'll be colder. And then you can generate a heat map based on that. And again, it's just a very powerful, useful tool for networking and analyzing your Wi-Fi signals. Next, we have Wireshark, which is a very powerful tool. This is another one of those industry standard type tools. This is an open source packet analyzer that can capture and inspect network traffic at a granular level, meaning super detailed level. And you can either capture the traffic and then analyze it, or you can just inspect a PCAP file, also known as a packet capture file. And this can, once you've generated your packet capture file, either using Wireshark or TCP dump or something like that, you can actually use Wireshark as a graphical user interface to analyze those packets on a much deeper level. This analyzes protocols and payloads. This detects abnormal traffic patterns. You would have to be the one to notice that it's an abnormal traffic pattern, but at the very least, it'll go ahead and detect it for you. It is fairly good at categorizing things for you. And of course, it helps you analyze the protocols for each individual packet. It'll help you analyze what payloads are attached to those individual packets. You can even download the payloads onto your machine based on the packet capture file that you have, and a variety of different reasons as well. So in the context of networking, Wireshark is a very useful tool. We also use it for pen testing and security analysis as well. It does require that the person that's using it knows what they're looking at, so you have to be good at investigating those packets and trying to figure out what's going on. But if you know how to use Wireshark, then you will be able to, follow along streams of traffic or the various conversations that are being had inside of that packet capture file, and you can use it to really diagnose and investigate a lot of different things. This is, again, it's one of those big tools that is used very frequently for a lot of different reasons. So we have diagnosing latency, which is the speed, and of course packet loss issues. So if that's indeed the case, you can try to figure out where it's happening, why it's happening. You can also use it to detect malicious activity like ARP spoofing or DDoS attacks, because you can again filter the traffic based on, if we know that DDoS attack includes ICMP packets, right, the ping packets. Based on that, we can filter for ICMP and see what's going on, and where the flood of ICMP packets is coming from. And then the thing that we talked about for ARP spoofing, where you can either disguise your MAC address, right? It's also known as MAC address spoofing, where you disguise your MAC address to actually seem like a legitimate MAC address so that you can bypass certain filters or certain firewall rules, and then actually connect yourself to the IP address that is blocked off using the firewall or whatever it is. There's so many different things that can happen as far as malicious activity is concerned that you can detect it using Wireshark, and you can of course use it to detect Nmap scans as well. There's a lot of things that you can do. So very, very powerful tool. We will definitely be using Wireshark in depth, and then of course there are other videos on this channel as well that include the beginner to advanced levels of using Wireshark and its different filtering mechanisms. So in this particular example here, we have a command line, the command itself that's actually using Wireshark to capture traffic on this particular interface. If you're using the graphical user interface, as soon as you load it up, literally on the very starting page, there's a section where you can pick one of the interfaces that are available on your computer and then just start capturing traffic. Super, super easy to use. And then, of course, very useful for investigations and diagnosis and so on and so forth. So that is Wireshark. The next one is SolarWinds Network Performance Monitor, and last time I checked, this was not an open source tool, so I believe this is a paid software, but it is a really big software. It's a very big name when it comes down to networking and just monitoring, and it provides real-time network monitoring, offering performance metrics, device statuses, and alerting. And SolarWinds in general has a suite of different tools. So the Network Performance Monitor is just one of the tools that falls under the SolarWinds brand. And it's a very big company. They are used by a lot of really big companies and government agencies. And they actually went through a hack. Somebody, I think it was Russia, that injected some malicious code inside of the source code for one of their updates. And all of the companies that used that update without verifying it had that injection attack embedded into their systems, and it was like a whole ordeal. But obviously ever since then they've patched it, they've resolved everything, and they are still to this day a very big name when it comes down to networking and network monitoring and everything else. Really, there's a lot of stuff that you can do with the suite of software that is available with SolarWinds. In this particular case, with this particular software, we can use it to monitor the bandwidth utilization of our various devices in our network, and we can proactively use it to identify performance bottlenecks, because again, it'll actually show you performance metrics in detail. It'll show you the statuses of the devices. It'll help you generate alerts depending on what your requirements are, and it'll monitor your network. So very, very powerful tool, very powerful series of tools from a very powerful company. All right, now we are at the hardware tools category. And these are obviously physical devices that are used for testing various elements of your network. The very first one is going to be the cable tester. And we've touched on some of these already, so these will be reviews. But we are going to introduce some other tools as well. So the purpose of a cable tester is to test physical cables for continuity, for shortages or short circuiting, and of course, proper wiring and connections. And we would use it to diagnose physical connectivity issues and verify newly installed cables and a variety of other things. But mostly it's to check the strength of a cable, like the actual persistence or the strength of the connection through that cable. The continuity portion of it is to just make sure that it actually is running smoothly from source to destination, the two different endpoints that cable is connected to. And it can actually identify where, if there is a cut or if there's some kind of a disconnection that's happening on that cable, it'll show you at what distance. So let's say it's 50 meters out. It'll show you that, hey, there's a disconnection happening. There's like some kind of an issue with this cable at 50 meters from where you're connected to. And then you can use that to try to troubleshoot and try to fix what's going on. Our next tool is the spectrum analyzer, which analyzes the radio frequency spectrum, the RF spectrum, to detect any interference to your devices, any interference sources. And this helps to identify sources of wireless interference, and it helps you optimize wireless network performance. And this is what it looks like. And this is a monster of a device, as you can see right here. It's a very, very cool device. Has a lot of different options. You can do a lot with it, including, of course, connecting your various devices to it, or just scanning for the devices in your area and trying to figure out what is going on with them, if there's actually any interference that's happening. And you can use it to get, as the gauge on the screen kind of varies, as the signal connection varies, you can actually pinpoint where the interference is coming from, and then follow that along so that you can hopefully alleviate whatever that interference is. You can remove that interference so that your signal re-strengthens, or your signal gets stronger again. So this is a tool from Keysight. It is called the UXA Signal Analyzer, and then there's a whole series of numbers right here. But again, just a really, really powerful tool. And yeah, this falls under the spectrum analyzer. So this helps you analyze radio frequency spectrums to actually detect interference sources. And then we have the loopback adapter. So we've already talked about the cable inspectors as well as the loopback adapters. So these are devices that simulate a network interface by sending traffic back to the originating device to see the functionality of the network interface itself, and then diagnosing device-specific network issues. So the loopback adapter essentially simulates an interface in your network, and then it starts sending traffic to wherever the originating device is, so you can see essentially if there's any kind of an issue within your network, and with the connections, the traffic that goes back and forth between your devices and your network devices, between your interfaces and your network devices, I should say. So these are loopback adapters. The best practices that we would have for this, obviously you want to use the right tool for the job, and this helps with honing in, right? Like narrowing down what the actual problem is, as we went through our troubleshooting philosophy at the very beginning of this chapter. You want to first figure out what type of issue you're dealing with, and then use the appropriate tool for that specific issue. So if you need to do packet analysis, you would use Wireshark. If you're trying to do a diagnosis on the path that the traffic is taking outside of your network, as it leaves your network, you would use Traceroute. Of course, to get the best picture, to get like the full picture of what's going on, you want to combine tools. So you want to cross-validate your findings and make sure that, one tool is just, sometimes they do give you different information. So for example, NSLOOKUP and DIG you would use both of those same tools to resolve DNS issues, and they essentially kind of do the same thing, but they have different data points that you can get from each one of those tools. So you can use ping to check the connectivity to a given host, and then you can use traceroute to diagnose the latency to that same host, because ping will also give you some kind of a latency response, but traceroute will give you a little bit more detail on that, and then it will also give you the full path that a packet is taking. Ping isn't going to give you the path that a packet is taking. It's just saying, hey, we sent the packet and we got a response. We sent the request, we got a response. Traceroute will say, okay, this is the path that your request actually took to get to its destination, and this is how that latency number was, how it came up, right? So it'll combine all of the hops that packet took. Ping will kind of just give you like a general, okay, this is the total response time that we actually got from this thing. And then, of course, document all of your results. This is, again, one of those repeating themes. So record your findings, test the results to build a troubleshooting history. From the very beginning, there should be some kind of a ticket that is created when there is an issue that is reported, and then you just follow along with that ticket until you have resolved whatever that issue is, and then you have this full history of what just happened and how you resolved it, and then you use that to create your troubleshooting history for future reference. And then we, of course, stay updated. So regularly update your tools to ensure compatibility with new protocols and technologies. And this goes for the physical tools as well as your logical tools, the software and command line tools that you would use. And, the tool that would test a copper wire obviously is not going to be able to test a fiber optics wire. So you need to have updated tools. And then same thing with your version of Wireshark, right? Like, so you should be running the most recent version of Wireshark. You should be running the most recent version of Traceroute, or fill in the blank. So you want to stay updated so that you have full functionality, as well as you ensure compatibility with the various technologies that are inside of your network. All right, time for some scenarios here. So scenario one is to the diagnosis of packet loss with ping and Wireshark. And the problem is that users report intermittent connectivity. So it's like connecting and not connecting. So number one, we would use ping to actually detect the packet loss if there is any. And number two, we would analyze the traffic with Wireshark to identify potential causes like congestion or hardware faults that are going on, which is causing this intermittent connectivity. Scenario two would be to resolve DNS issues with NSLookup, and the problem is that users can't access websites, which is clearly a DNS issue. So we would verify the DNS server configurations using NSLookup or DIG, and I would say DIG will probably give you more details on your configurations than NSLookup itself would. But again, if it's a DNS issue, you are using NSLookup or DIG to try to figure out what is going on. Scenario three would be to scan a network for security risks with Nmap, and the problem is that the company wants to assess its vulnerability to attacks. So we would use Nmap to identify open ports that should not be open, and to identify outdated software to find any vulnerabilities if we possibly can. So Nmap is great for enumeration, as well as trying to identify open ports. Basically, any open port is an extra vector, an extra attack vector that somebody can take to try to attack our network. And if we are not using the port, if there's nothing that is critical about it that we need to close all of those ports. It's a part of security hardening. So you want to close all of the ports, shut down all of the services that you are not using to shrink the attack vector to as small of a surface as you possibly can. Scenario 4 would be optimizing Wi-Fi performance with a Wi-Fi analyzer. And the problem is that there's poor signal strength in certain areas of an office. So we can use a Wi-Fi analyzer to identify interference and optimize channel settings. You can also use it to look at the heat map, for example, and try to see what the heat map is for your Wi-Fi signal and see what is causing poor signal strength in certain areas of the office. Scenario 5 is locating faulty cables with a cable tester. And the problem is that a workstation loses connectivity intermittently. So we want to start as the physical layer, right? So that would be the very first thing that we want to look at is the cabling. And so we would use a cable tester to detect wiring faults or discontinuities after we have visually checked if the cables are not cut or if there are any disconnections taking place or so on and so forth. Once you've looked at the physical cables and you see that they're fine, you'll be like, all right, let's use a cable tester to actually detect the wiring itself and see if there's any, maybe inside of that plastic casing that's wrapping that cable, maybe there's some kind of a disconnect that's happening there. So we would use the cable tester to find wiring faults or discontinuities. And this brings us to our last set of practice questions here. So, which command line tool is used to test the reachability of a device and measure latency? And that would either be ping or traceroute. NSLOOKUP is for DNS records, netstat is for open connections and listening ports, etc. So I would say ping or traceroute. Now in this particular case, it's saying testing the reachability of a device. So I would narrow it down to ping. Very good. What does traceroute provide? A detailed DNS record? No. A list of open ports on a device? No. The path and delay of packets to their destination? Yes. Real-time bandwidth usage? No. So answer is C. Which tool would you use to analyze DNS resolution issues? So again, NSLOOKUP would be for DNS, Nmap is for network enumeration, open ports, Wireshark is for packet analysis, ipconfig is just to see what the IP address that is connected to your specific device is, like what your actual IP address assignments are, what subnet you belong to. So DNS resolution would be NSLOOKUP. What is the primary purpose of Nmap? Capturing, analyzing network packets? No. Mapping networks, devices, services, and open ports? I would say yes. Testing wireless signal strength? No. Monitoring network bandwidth? No. So mapping a network. Network mapper maps the network devices, services, and open ports. Which tool is best suited for analyzing wireless interface and signal strength? So analyzing the wireless interface and the signal strength for it, we would use most likely the spectrum analyzer because it's looking at the radio frequency to see if there is any interfaces interference. Is looking at that to see if there's any interference. Very good. So what is the role of a loopback adapter in troubleshooting? Testing connectivity between two remote devices, simulating network traffic for stress testing, sending traffic back to the originating device to verify interference function or interface functionality. I would say that would be the answer. Capturing, analyzing packets, that would be no. So it's going to simulate an interface, right? And then it's going to send traffic back to the originating device to see what the functionality of that entire setup is. Very good. So which tool can identify the root cause of high latency and packet loss by analyzing network paths? So we're looking for latency, right? So meaning it's taking too long. If it's high latency, meaning the time to reach its destination or to do what it's supposed to do is taking too long. So we want to identify the high latency as well as packet loss by looking at the path of the network. So we are trying to trace the route of those packets. That's exactly what we would do. What is a common use for Wireshark? So to detect misconfigured DNS records, analyzing packet level network traffic. I mean, that's literally a packet level network traffic. Scanning a network for open ports, testing physical cable. So it does not scan a network for open ports. It listens to traffic that's going on inside of a network, and then you can see if there are open ports based on that traffic. It does not test physical cable continuity. It can detect misconfigured DNS records. That could be something that you can do with the packet capture that's being done with Wireshark, but its main purpose, like its common use case, is to analyze packet level network traffic for anomalies. What information does ipconfig all provide? So ipconfig is for Windows machine /all, gives you all of the data, including all the IP addresses, all the subdomains, all of the IPv4, IPv6, the subnets, etc. Oh, excuse me, not subdomains. I should have said subnets. It gives you all the subnets, the IPv4, IPv6, the interfaces, IP addresses assigned to them. So network path and hops, no. All of DNS records for a domain, no. Comprehensive details about the local device's network configuration, that's pretty solid. Current state of all active network connections, that would be netstat. So C is our answer here. Which tool would you use to detect a faulty Ethernet cable? And that would be our cable tester. Nmap is a logical tool, ping and netstat, these are all logical tools. Cable tester is the only physical tool. And that's it. That's literally the last question that we have for this particular section. and we are now officially done with all of our lecture material. So now we actually get to go into our practical exercises, and we will be going through the various tools that we're going to be using to understand everything that we have talked about so far. So this is it from this moment on. It's pretty much going to be the practical exercises that we're going to be running with the variety of tools that we have. So, for example, Wireshark is going to be the very first one that we're going to use. We're going to capture some network traffic. We're going to identify packets, and we're going to determine how those packets correspond to the various OSI layers and how to actually read the packets and recognize them, etc. So let's get into the practical stuff. To get access to the Network Plus notes, as well as the mock exams and the practice questions slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training.